Yeah, no problem.
Yeah, we can do it afterward.
Ya.
Yeah. Hello. That's okay.
Yeah.
Although, I might be wandering a little bit.
Sorry?
I might be moving a little bit.
Yeah.
Seems like there is another microphone.
Okay, you can put on the microphone.
Yeah, I think I'll. Oh, that's the mic. Okay, yeah.
Yes, it's...
Yeah, so then I'm not tight.
Ah, ¿qué hice? No sé qué hice. Yep. Over here or there.
Hello? Enough? Is that enough for the? Okay. Oh, I'll be away from.
Okay, thank you everyone for coming to the last day of the workshop. So my job today is to keep the time, on time. So I'll try to do that. We started already 2 minutes late, but that's okay. We move everything all the talks 10 minutes.
20.
20. Oh yeah, 20. Oh, you're lucky. So today's talk is by Professor John Bench-Hopper. And the talk is about what can Maxwell demons do. So this is our first talk. Thank you very much for coming, and then I'll give you 20 minutes signal, I guess, or 15 minutes.
Okay.
You have the 30 minutes.
It's the 30. It's the 30 minutes. Yeah.
30.
Okay. Well, again, I wanted to thank Gabriel and Jose Daniel for the invitation to be here. And so in the first part of the week in the school, I went through a lot of things in control theory with the promise that it would have something to do with stochastic thermodynamics. And so I hope that you'll see in a couple of places those applications coming, being delivered. Okay, so the work that I want to talk about is some experiments that we've been doing on a kind of realization of a Maxwell demon. And most of the experimental work, well, actually, the only experimentalist on it is Tushar, who finished his PhD about a year ago. There are a few little contributions by other students that we'll talk about as they come. We were very lucky to have an active group of theorists in the same department, led by David Sivak. Yannick Eric was a postdoc with the two of our groups, but contributing primarily on the theory side. And Joe Lucero was a master's student who also was a theorist in this. Okay, and I should say this is our part of the world, way up in the corner of North America. Okay, so it was working much better. Okay, so the outline of what I wanted to talk about is to present our version of a Maxwell demon and tell you how it works, and then to tell three stories about work that we've been doing it. One on sort of viewing it as a motor. What are the performance limits? It's a new kind of motor powered by information about the environment, and it differs in properties from traditional motors. So we'll see about the power extracted, energy extracted from a thermal bath, how fast it can go, and so on. And then think about the effects of measurement noise. And this connects very closely to what I was talking about yesterday, or Wednesday. And then finally, to think a little bit about what happens if you take this engine and put it into an environment that has extra fluctuations beyond just thermal fluctuations. Okay. Okay. So to get started, I think most people will have seen some version. It needs to be up. I mean, for this room, I can just talk louder too. Okay. So for, I think many of you remember the sort of classic version of the Maxwell demon, where you have a little demon that sees gas molecules and sorts them according to their speed. we wanted to make a kind of simplified version of this that we could realize experimentally. So conceptually, the version that we're doing just looks like, imagine that you have a heavy mass hanging on a spring from a support, okay? But the mass is small and it's in a fluid, let's say, so it's vibrating up and down, and you can see those vibrations somehow. And when it fluctuates up and down and hits a threshold, the spring is compressed. You have a demon that is watching the position, measuring the position of the bead. And at that point, the demon lifts up the support. And if it's done just right, the energy of compression will equal the energy of stretching here, the spring. And so you're not doing any work. The energy of the spring is the same. However, the equilibrium point has now gone from here to somewhere up here. And so we can sort of repeat the cycle of fluctuating particle in a bath, wait for an up fluctuation, raise the platform without doing any work, and repeat. And we're, you know, we're lifting a heavy mass in a gravitational potential without apparently doing any work. So that's kind of the essence of the Maxwell-Demon sort of quote unquote paradox. Now, we realize this experimentally with optical tweezers. So we have a focused laser beam that is horizontal, so going like this, and a heavy particle in gravity, so it's sinking a little bit below the center of the beam, and then it goes and we raise the beam, and so we can realize this setup with an optical tweezer. Okay, and I know this is mostly a crowd of theorists, but there's typical equipment involved. I guess the main thing that's a little bit special is that we have to do this kind of feedback loop that we're running, because really when you're measuring the position and then deciding to shift the beam, that's a feedback loop. And so that's running at 50 kilohertz, so it's 50,000 times a second, so it has to have specialized hardware to go that fast. But apart from that, this is fairly simple. That's in this FPGA controller part. Apart from that, it's fairly standard stuff. And we have a very fast way of sort of shifting the beam direction and basically the beam position here. Okay, so the feedback rules that we're using look something like this. If lambda is the height of the beam at time step n, because everything is done digitally in discrete time steps, then if the distance between the position, which right now we won't distinguish between the true position and the measured position, we'll assume that they're basically the same. We look at that relative to the beam position, and if it's fluctuated above an amount xt relative to that beam height, then we raise it by an amount that has an adjustable parameter alpha that I'll come back to. Otherwise, we just let it sit. And so that algorithm applied here, you can see x minus lambda, and this is the amount that we raise it, will lead to trajectories that look something like this, or this is an example. So this is the lambda, the beam position, and every time the height fluctuates a little bit up, then it follows it. But if it fluctuates down, it just waits for the next fluctuation up, which in this case doesn't come until here. So you get this kind of staircase ratcheting kind of trajectory. And I guess one thing just to notice is that the scales here are fairly small. This is 20 nanometers, and this is 1 millisecond in time. So this all happens quite fast, and we can get a lot of statistics, which is good for these kinds of measurements. Okay, so the first question is, how do you choose this gain? The naive way to choose it would be expressed in this picture, that this is kind of sideways. So up is in this direction. So the fluctuation is now in this direction. So if it's fluctuated to a certain amount past the center of the beam, you would say, okay, we want to ratchet, and we move it just the amount so that the energy is the same. In this coordinate system, that corresponds to alpha equals 2. Sort of, we're going this distance and then another distance away. However, if you measure the work, which we can do by looking at the change in the stretching of the spring, when we whenever we move the beam height, we're like moving the support, and so then we're changing the spring stretching and changing its energy. And so that's the work that we're doing. So we can actually measure this stochastically as we go through and look at the average. And if we compute the average here, I'm expressing it as a power in terms of KT and the relaxation time of the bead in the trap. What we find is that it does indeed go through 0, but not at alpha equals 2, but a little bit lower. And one intuitive, there are actually 2 reasons for this, but the intuitive one that I'll mention right now is that there's always a delay in these operations. So when I say you see it hit a threshold and then you react, you can't react instantaneously, or we can't react instantaneously. And so the bead on average will slide down a little bit. And so then we would move it a little bit less. Okay, does that make sense? All right, so we'll come back to this because that's actually only half the story. So now we have this device and we know how to tune the feedback loop such that, we're doing this. I should say, of course, that, the resolution to the Maxwell-Demon paradox, because this seems to be, we're taking a particle that is connected to a single heat bath and extracting work from the heat bath. And second law says that if you just have one temperature source, that shouldn't be possible. But of course, we have a measurement system and a control system all working in parallel. And so the cost of those measurements, you can show, always has to equal or exceed what you're getting from the bath, at least in this kind of setup where we only have one temperature. And in our case, we're not worrying about this, so our costs are huge compared to what we're getting out as work. Okay, but that's not our focus. Our focus is more just, we have some method for doing this, and now what can we make it do as a kind of different kind of engine? So as this thing is ratcheting up, the free energy of it is which is basically, in this case, gravitational potential energy is increasing. And so we can look at this rate of increase, and this is the power that we're extracting, work per time that we're extracting from the heat bath. And we could try to maximize this as a function of various parameters. So one parameter is this threshold about how much do you go above the beam height before you start to, before you do the ratchet. So here, and the first thing we find is that it's better to, that's the second thing that we find, is that it's better to make this threshold equal to 0. The first thing that we find, we can ask, how often should we do these measurements? So we have this loop rate that we can control. And so we can make it go faster and faster. And in the beginning, the faster you do this, the more operations you do per time, the more power you extract. But at some point, it saturates. And the basic reason is that there's we'll come back to this a little bit, but there's an equilibrium relaxation time. And let me show this on the next slide. But we maximize it first by going to very high sampling frequency and by minimizing or setting this threshold to 0. So that what it's basically saying is that whenever this bead, the moment it goes above the line here, we want to ratchet up. You don't want to, in this kind of setup, you might think maybe we should wait for a very large fluctuation to take it and then just take advantage of those large but rare but large fluctuations. And in this case, that's not the right thing to do. Okay. All right, so as I said, the time scales here are scaled by how long it takes a particle which has overdamped dynamics to relax down to the center of potential. That's given by tau r, which is related to the fluid viscosity, the size of the particle, and so on, the stiffness of the spring. And so we get a characteristic power, which is kT per relaxation time, which have energy of order kT, and the bead can only respond on a time scale tau r. And so basically, the fluctuations that are happening on a faster time scale, or the sampling that we're doing on a faster time scale, don't give us independent information because the bead just can't react that fast. There are thermal fluctuations that are faster, but the bead just averages those out and can't respond because it's got a finite size, it's in a viscous fluid, and there's a time scale associated with that. Okay, so then we can make measurements, for example, of the velocity. This is different bead size. This is increasing the stiffness of the trap, which means turning up the laser power. We can measure the power that we're extracting. And if you do it, sit down and work out the theory of this, which I'm not going to do, this is an experimentalist talk, but basically we look at this as a kind of first, or the theory, half of us looks at this as a kind of first passage time, where after you ratchet, let's say you're here, and you have to wait for a fluctuation here, so you're calculating a first passage time to go from the threshold, the old threshold, to the new threshold, and so you can, these are actual physical units like kT per second, and notice that we're getting like 1,000 kT per second. So these are significant amounts of power. They're comparable to what biological motors produce and so forth. But then we can write things in scaled units. This is velocity scale. There's a typical fluctuation length scale, sigma here. So if we take that as our length scale and tau as our time scale, then we have a dimensionless velocity. And similarly, we take kT per tau. And here we're plotting it against sort of a reduced mass, which is the buoyant mass in the fluid scaled by, it's basically scaled by it's measured by how far it sags down in the, you have the equilibrium position, and then with gravity you sag down. So that gives you that length relative to the fluctuation length is this quantity here, and is proportional to the mass. Okay, so in these units, all of these curves collapse, and this one is particularly interesting because it says that to extract work, there's actually an optimal size. And basically, it's a balance between, if you have a particle that is too small, then the speed that you can go increases. But of course, the energy, the gravitational potential energy is very small, goes as the volume. So when it's too small, there's not very much energy that you're extracting. On the other hand, if it's too large, then the fluctuation that needs to go from sort of the equilibrium sag point to the center of the beam takes too long. Okay, and so then that meets you over here. Okay, so we have an understanding now of how to maximize, for example, the power out. So this is again in units of kT per tau r, and it's about 0.3 in this. And so that was sort of our first goal. Actually, if there are any questions, this is a good stopping point. Yeah.
Is there anything in your setup that you could change to move the beat on this last one?
Sorry, here?
Yes.
I mean, well, two answers to that. The first answer is that this is these are in scaled units. Okay, so when some of the obvious things that you can change in the setup that would make a difference are already kind of accounted for here. So the point is that given for example, what this shows is that if you increase the stiffness of the trap, okay, and the stiffness is proportional to the laser power, so you're just using a brighter laser to do this in this case, then there's subtlety about heavy beads in the beginning are no good, but then they're better and so forth. But all of these curves are increasing with trap stiffness. So one answer is just to make use stiffer materials to make it the trap. We'll see another answer at the end of the talk, so we can hold off for that. Okay. So the second thing I wanted to talk about is the effect of measurement noise. And here, this is the original situation that we talked about, except that as I was trying to distinguish in this lectures earlier the week, we can distinguish between the true position, which we don't know and will never know, and the observed position, which I'm expressing here with just the true position plus additive Gaussian noise. And so this is sort of blurred out in a schematic way like this. So we don't have access to this. We have access to something like this. And then the question is, what happens when you start using something like this in the information ratchet? So the first thing is to think about there's a kind of signal to noise here. So here's the trap, the parabolic potential of the trap, and there's an equilibrium Gaussian distribution in the trap with size sigma. But now we have a second Gaussian distribution which characterizes the noise, so that given a true position, if we make a measurement with our, I haven't really talked about our system, but it has noise like any system. And so we would, and it's roughly Gaussian in our case. So we would have another Gaussian distribution whose standard deviation sigma m characterizes the width of the noise, and their ratio is a signal to noise ratio. I'll call it signal to noise ratio. Okay, and we can change this systematically in our experiment by reducing the intensity of the laser. Okay, so back to this scenario here. So I talked about looking at the amount of work that we're doing when we raise the platform, and we're trying to tune this to 0. And so we had a story of we expected it to be 2, and it actually went through 0 at roughly 1.5. And I said, well, that had something to do with delay. And there was this picture here. As I said, that's only half the story, though, because this was done at a signal to noise ratio of 11. And now we can, which is pretty high, and we can vary the signal to noise ratio systematically now by changing the intensity. So as we do this, what we see is that as the signal to noise ratio starts from 100 and goes down to almost 0.1, that this crossing point here, the value of alpha, this alpha star here, which was 1.5 at a signal to noise ratio of 11, now actually depends on the signal to noise ratio, and in a fairly dramatic way. So we can see that if we go up to really high values of signal to noise, it's about 1.8. So that part is the part that's associated with the delay. The rest of this somehow is associated with the signal to noise ratio, with the noise of the measurement. And so that's, I want to try to justify that a little more. Well, you can sort of see it depends on the signal to noise ratio. And then there's this dramatic transition where you may be able to see that these are, I tried to write these with hollow symbols, and I'm going to suggest that these are actually 0 and not just a very small number. And that this represents a kind of phase transition that's happening. Okay, so the way to figure out if it's 0 is we've been looking at this curve, a curve like this, in a small region around the 0 crossing. But what it actually is like schematically is something like this. This is the scenario that we think is going on, which is that when you have a high signal to noise ratio, when there's not very much measurement noise, then we have a situation like this. But we also know that if you set alpha equal to 0, that means that you're not doing any ratcheting. It's just sitting there. So then W dot also has to be 0, and that's always a solution, right? You always have the option of doing nothing. And so this point here always has to, so it connects something like this. But it could also connect like this, in which case there's only one solution, and then that's to do nothing. And what I claim is that what's going on as we change phase transition is that at high signal noise it's like this, but then it's gradually evolving to be like this. And when it just hits the flat intermediate stage, there's a transition between a solution of alpha that is larger than 0 and one that is 0. And in order to see that, we have to kind of go and look at this region here, which we did. And whoops. Yeah, sorry, here. So we're looking here just in the neighborhood. So these are very, very small values of alpha. And we can see that as a function of signal to noise, which is represented in gray level here, it's transitioning from high signal to noise here to low signal to noise. And if we look at the slope, the initial slope here, we get something like this, and it extrapolates through. And at this point, we have a critical value of the signal to noise and a kind of phase transition. So it's a phase transition where the engine basically stops working. So if we measure the f dot that we're able to get, so there was a maximum. We're not working quite at the max, the highest value of maximum, but we saturate at some large value of signal to noise at what we would expect when we don't take into account measurement noise. And then as we, these are experiments, that's a simulation here. As we reduce the signal to noise, this goes down, but here it really stops. And in this region, basically, we're just never ratcheting. And so it's a transition where if the signal to noise ratio is too low, there's a transition and then the engine just stops working at all. Okay. As opposed to just sort of fading out. I mean, we sort of expect that if you make noisy measurements, somehow you're going to be able to get less out of it. What was unexpected, at least to us or to me, I'll put it that way since that's a personal thing, was that it would just stop in the way of the phase transition. Okay. How to understand sort of what's going on. The claim is that this is due to a kind of bias in the measurements or bias that happens when you're just using measurements naively. So let's imagine that we observe the bead at this position, which is just at our threshold. Okay, and we're trying to decide, should we raise it or not? Okay, my claim is that if you see it here, okay, it's actually most likely to be below the position. So it's not an unbiased measurement. It's a biased measurement. And the reason is that this can happen schematically in two ways. This is the equilibrium position. We could have a fluctuation up here and a noise negative. Remember, the noise can be negative or positive with equal probability. Or we could have a fluctuation to here and then a positive noise fluctuation. So the noise, it's 50-50, but this kind of fluctuation is much more common than this very rare large fluctuation. And so this scenario is more likely to be occurring than this one, which means that on average, you see it here, but on average, it's down here. And it's that bias that is messing things up. It's why we had to correct the value of alpha to compensate for it. And the phase transition is happening when basically the correction is so much that you'll be going down negative, but you never want to go down negative. You always have the option of doing nothing. And so that's the essence of the phase transition. Okay. So then the question is, can you do something about it? And the material that I talked about on Wednesday gave the outline of what's an alternative strategy, which is to use this Bayesian estimate of where the system is, which in this case turns out to be a Kalman filter. And so we can implement a Kalman filter. So we're not just using the naive measurement in the feedback loop. We're actually running a Kalman filter, making our best estimate, which uses measurements going back into the history effectively. And then we can get actually an unbiased, I mean, the main thing is that we're able to get an unbiased estimate that way. So when we do that, we find that this curve, if we go back to our high signal to noise case, the curve that went through this, if we didn't use the Kalman filter, now goes exactly through 2. And indeed, you can do this for any signal to noise ratio, and it's always 2. So what then happens is kind of interesting. Before, when we used the measurements naively, we went down and had a phase transition. Now, with the Kalman filter, it just smoothly fades away. Okay, and so the phase transition, in some sense, was a result of having this bias that happened. And what's interesting is that if you take the difference of these curves, it looks something like this. And this is a pretty substantial. This is half the power that you can get with the perfect information. We're getting at signal to noise ratios which are under just a little bit under 1.7 or something like that. And to me, that's kind of remarkable. It's saying that even though every time we measure the position, our errors are on the order of the natural scale of real motions. Okay, so or even a little bit bigger, we're still able to get half as much power out as we could if we had perfect measurements with no noise. So I think that's pretty remarkable. And the benefit, though, only is really important right around this critical value of signal to noise, because if you have very high signal to noise ratio, then none of this matters, and you have very accurate information. And if really your noise is infinite, well, there isn't any information to extract anyway. But where this kind of sophistication, or taking a more sophisticated approach, can help you is right around this sort of unit signal to noise ratio. 2 minutes. Okay. All right. Okay. I had one more topic I wanted to talk about, but let me just briefly mention that we can take this information engine, not change anything at all, except that we put it in an environment that, instead of being in thermal equilibrium, has extra noise added. And in our case, the extra noise, it's we take a resistor and we amplify it over a band, And so the fluctuations as we put in the amplifier, and then it's applied to electrodes, which apply electrical forces that are fluctuating, but represent a non-equilibrium noise. And if we take the ratio of the standard deviations as our ratio of variances as our control parameter, then what we find, let me skip this part, because this has to do with the color noise, but let's just assume that the noise over the range that we can see in the experiment is roughly white. It's not perfectly white, but it's pretty close to white. And so we can treat it as white. And so it's kind of like having an effective temperature that we can then raise. And so as we raise this effective temperature, we're getting more work out. And the amount of work out that we can get is really only limited by the magnitude of the non-equilibrium fluctuations. And the maximum mass increases as well. But what's interesting is, and this for the moment at least is still just theory, that the minimum power to run this is pretty much independent of this non-equilibrium environment, saying that you can have a non-equilibrium environment but still have your measurement device be at room temperature and not be affected by this environment. So its costs are pretty much independent of this fluctuation, whereas what we're getting out increases, which means that at some point you cross over and you can do your measurements. You know, I said that the Maxwell demon was a losing gain. That's only in equilibrium. If your system is effectively at a higher temperature and your measuring device is at a lower temperature, then it becomes like a heat engine. Okay, but then you say, okay, fine, we know about heat engines. But the remarkable thing here is, if I put this on the thing here, is that you can have huge effective temperatures, far bigger than a real physical temperature. So, you know, a gasoline engine, you can have a 2-to-1 ratio of temperatures or something like that. Here, we can go to 10 to the, we're working at temperatures that have effective temperatures of 10 to the 4 K with measuring temperatures that are of order 10 to the 2 K. So you can have a huge difference there. And I think I'm getting to overtime. You can start to make connections between this and biological motors. But just to kind of summarize everything, I've told you about this sort of conceptual version of a Maxwell demon that we've implemented with optical tweezers and how to maximize the power that we get out of it, for example. There's some interesting stuff with phase transitions when you look at noisy measurements, and learning if you use a Bayesian Kalman filter, you can do better. If you put in a non-equilibrium environment, you can get more power out than you might put in, and so that has applications to energy harvesting. Sort of at the center of this, these ideas of control theory that I was talking about, sort of, I mean, if you've been paying attention, sort of play a role in a lot of different aspects. So, okay, anyway, thanks for now.
Thank you very much for the nice talk. No, I wanted to ask you. Okay, this is the higher the efficiency curve with bias filter. What is the one without the bias filter? Only with the naive approach.
Sorry,
The green one. That green
this one.
Yes.
Sorry, this is the difference.
Ah, that is the difference.
This is the difference.
Okay.
So 0 means that they're basically the same.
Yep.
And then when it's positive here, you're getting an advantage.
Ah, okay. Thank you. Yes.
So, or,
So I have two questions. So first one is, have you tried to check like fluctuation theorems for with information for in your setup?
for this setup, no. I mean, we did a previous set of experiments on modeling 1-bit memories and erasing and so forth, and there we did. For this one, we haven't really looked at that so
Okay.
far. I mean, if there's an interesting question to ask, I mean, people have looked in feedback systems, so it would have to be, you know, maybe there's something more refined that would be interesting to look at.
Okay. So for me, what is interesting here is that you apply the feedback at a stochastic time, right?
Um, yeah, I mean, the rule effectively amounts to that. Yeah, I mean, of course, I mean, another way to look at it is that it's a nonlinear, we're applying it at every time step, but there's a step function with a threshold. And so you could sort of think of it as like a nonlinear feedback applied at every time, or I suppose a linear feedback applied at a stochastic time.
But the fluctuation theorems, at least the usual one, nobody, Sagawa, Noel, and these people are always like at a fixed time.
Yeah.
So it's,
Okay, well, that might be an interesting way to look at it. Yeah, I agree.
and the second question is in the case of an unequilibrium environment, so how you manage to measure heat and work?
So here we're just doing everything exactly the same that we were doing in an equilibrium environment. So the work is measured just by the amount that we raised the particle. So it's now available as gravitational potential energy. I mean, we haven't really directly looked at heat. I know there's some subtleties in how one should define it and this thing. So I guess we've just sidestepped those at least for the moment.
Okay, thank you.
So this is a quite general aspect, no? So using the bias to predict the future, no? Will increase the efficiency of these systems. So my question is, how did you do for the feedback? Because you have to compute the bias and so on. How do you do it? You were controlling everything in the computer, and the computer was computing the bias, or did you have to make a small circuit for that? It was
No, it's done on the computer.
okay. And this was the. I
I mean, I
guess it
should say
was
it's done on
the
this
frequency limit.
the special hardware that's really designed to do these things in real time. So it's not like an ordinary PC. I mean, it could be done in an ordinary PC, but we were doing it on the special thing so that we could do everything very quickly and particularly with controlled timing. So in a PC, when you do calculations, it's always time sharing this and that, and so the amount of time something will take can fluctuate a lot. And we're using special hardware, which is actually slower than a PC, but more predictable in its timing.
What did you use? What did you use?
It's called a field programmable gate array.
Uh-huh.
So they're in almost every electronic device these days. But they're basically a set of digital logic gates that you can sort of program the connections and turn it into a little computer and make it do, but a computer that's just doing the calculation that you ask it to do.
Great.
I think we have finished the questions.
Okay.
So, thank you very much.
Okay, thank you. Okay, thank you.
Maybe later when there's time.
Sure. Oh.
Okay, so the second question for today is done by Carlos Albert. Thank you about and this numerical integration of class and plastic integration and singular
Hello, does everybody hear me over there? Oh, okay, excellent. Hello, everyone. Let me share my screen then. Okie doke. Does everybody see my screen? Hello? I don't hear anything from Bogota. Does everybody hear me? Yes, now I can hear you. It's a bit faint, but I can hear you. So may I start? Oh,
Okay, Sergio. I already announced your talk, so the floor is yours.
oh, thank you. Okay, good. So let me start by thanking Jose Daniel and Gabriel for their very kind invitation. It's really an honor and a pleasure to be here. I mean, to be talking to you. I wish I were there. I really miss Bogota, and I would like to go back soon. My talk is more about numerics. It's a bit removed from physics, but the idea is that uh, some of the research that I'm doing lately is about numerical integration of stochastic differential equations. In particular, those that have singular drift. So you know how in a stochastic process you have the noise term and the drift term. And most of the time, these two terms have to be more or less well behaved if you want to do simulations that are reliable. However, there are problems. Sometimes you find drifts that are singular. So there are drifts that explode. And in those cases, the numerical integration techniques that we know now are insufficient. However, in doing my research, I derived a method that I, at the beginning, thought was new, but it turns out that it had been discovered in the 80s by a couple of Russian mathematicians. I will introduce that to you soon. And what's good about this is that in the class of processes that I am considering in this work, in particular the Dyson model, this method is particularly adept at taming the singularity. So what that means is that where the singular drift is supposed to explode, there is a term that actually controls the drift function and keeps it, let's say, bounded in such a way that it makes the simulation stable. So let me begin by introducing the problem with a bit with a bit more context. So normally in statistical mechanics, in particular non-equilibrium statistical mechanics, we like to model certain situations, certain systems using SDs or more specifically Langevin equations in physics are what we use the most. But at the end, you can think of them as equivalent objects. And in those cases, sometimes, well, solving a Langevin equation may be simple in certain cases, but in general, you don't have the tools, or rather the analytical tools to solve them exactly are somewhat limited. So in those cases, what you want to do is you want to do numerical integrations to run Monte Carlo simulations and see what you can calculate from there, or if you want to find out about an expectation, an expected value of some observable, you can run your Monte Carlo simulations and approximate whatever it is that you want to find. However, as I was saying before, if you assume that your stochastic differential equation looks like this, so this sigma here is the diffusion coefficient, and this b here is the drift coefficient. This is the more general version where the drift and diffusion coefficients are time dependent. But here in this talk, I will assume that time does not affect either coefficient. If you look at this SDE and you look at most stochastic analysis textbooks and even numerical analysis textbooks. The celebrated Claudin Platten textbook mentions this as well. The diffusion and the drift coefficients are supposed to be well behaved, where well behaved here means precisely that the functions have to be bounded, and Lipschitz continuous is the correct wording. All you need to know is that a Lipschitz continuous function is kind of like a function that has a well-defined derivative, and that their derivative is bounded. Think of it like that. That's not the exact definition, but as conceptually speaking, that's more or less what it means. So, if you look at an object like this, then you realize, well, if I were thinking, say, for example, some sort of stochastic dynamics of colloids, charged particles, you would think of a background that produces a Brownian motion and an interaction that looks something like the Coulomb force, say in 2D or in 3D. And in those cases, the Coulomb force is, of course, as everybody knows, is a function that explodes when the distance between the objects that are interacting tends to zero. The Dyson model is one such model that has that sort of structure, and a Brownian motion plus a singular Coulomb potential times the increment of time. Now, funny thing is, the Dyson model is very well known from random matrix theory, and it's been researched with using analytical methods for a long time. However, in many cases, we don't have the numerical tools to investigate them. The latest paper is by these two guys, Ngo and Taguchi, from 2020, and they found a semi-implicit formula to do these types of numerical integrations. However, their method, while theoretically interesting, is not currently it's impossible right now to implement it because you're required to know the future. So it's non-causal, let's say. So that was a problem. Then you go look for possible solutions in the literature. And for example, in the Claudin-Platten textbook, you see things like the Hune method, the Milstein method, the higher stochastic Runge-Kutta methods, and so on and so forth. And most of them, they require, okay, here there's a bit of a change in notation. This is a screenshot from the Claudin-Platten textbook. Here, the diffusion coefficient, sigma, is changed by the letter B. So B here is the diffusion coefficient function, and here you're required to have a derivative. In our case, because we're looking at an object that has a constant diffusion coefficient, this term dies, and so you get back to what everybody uses, which is the Euler-Maruyama method. It's the stochastic Euler method, let's say, which is not necessarily guaranteed to work with singular drifts. So in those cases, you don't know whether your stochastic integration will converge, and you need a different approach. So that's when I decided to look into this further and look at the most basic of the processes that look like the Dyson model. So consider the Bessel process. The Bessel process is given by this object here. It's a process that is given by a Brownian motion plus a repulsion from the origin that goes like 1 over the value of the process. Now, why is this process interesting? Well, it turns out that there is a model in mathematical finance that allows people to sort of look at how interest rates evolve in time, the CIR process. And so because of that, this Bessel process is widely known in finance, and they have lots of different numerical techniques to analyze it. So anyway, the idea here is, well, if you want to do a better approximation than just using the Euler method, you can try and integrate the steps of given by this as dE by integrating between 0 and delta t, the function, the right-hand side. This first object just turns into a Gaussian increment, and this term here, you can expand it. You can do a Taylor expansion. Once you do the Taylor expansion, you integrate over the variable s here, and you get this term. So here I am cutting off the Taylor approximation to first order. The reason for that is that on both sides of the equation, I get a delta x. The stochastic increment of the process appears on both sides. So I can easily solve for this increment, and I get what you see here on the right-hand side. Now, the good thing about this is that, for instance, if you look at this side, here you get a singularity when xn tends to 0. However, you are dividing this object by something else that has a higher order. This is 1 over xn squared. So the closer you are to the origin, the stronger this denominator becomes. And in the end, this denominator controls the singularity here, which is excellent. Once I went back to the literature and looked at whether somebody had done this before, it turns out that Averina and Artemiev, these two Russian mathematicians, did that in the 1980s. If you try and look at how the Euler-Maruyama method and the Averina-Artemiev methods compare when it comes to convergence, as you make the time step smaller, the Averina-Artemiev method is consistently better than the stochastic Euler method by far, and the stochastic Euler method is clearly not very consistent. So it's worth looking at this old method to see if we can maybe try and perform better numerical integrations of the Dyson model. So then, what happens when you go from the Toyer model, which was the Bessel process, to the Dyson model? Well, what happens is that you get similar equations as the ones I showed you before. However, the second derivative that appeared in the previous slide in the denominator now turns into a matrix. It's actually a Hessian. And so this Hessian goes here as part of this inverse matrix, which means that, sure, you still get the advantages of the one-dimensional Averina-Artemiev method. However, now every time that you try to calculate one stochastic step of the Dyson model, you have to perform a matrix inversion, which means that at higher dimensions, you are going to have to spend lots of time computing an inverse matrix or solving a linear system. However you choose to proceed, you'll still get an order of n squared. Yes, each time step will be of computational cost n squared, more or less, which is prohibitive when the system size becomes large. And so, well, you can still implement it though, and in the case of the Dyson model, the Averina-Artemiev method, as you can see here, the convergence is still better. You get not necessarily faster convergence, but you get, say, 2 orders of magnitude better convergence, even though as the time step goes down, it's not like the Averina-Artemiev method goes down any faster than the Euler-Maruyama method. However, it's still a very good method to use. Now here, okay, 2 minutes left. Thank you. Now in order to address the problems with how long the computation takes when you do the full Viernes method, I decided to try and instead of in the Dyson model, of course, instead of looking at the coordinates themselves, I tried to look at the spacing between particles. And so if you look at the spacing between particles, you get this stochastic differential equation, which looks very much like a Bessel process with an extra term here. In this extra term, well, in order to simplify the method, I decided to make the following approximation. Only the one increment that I'm looking at changes when I integrate this part, and the rest of the increments, the rest of the spacings remain the same. So it's a bit, it's kind of a ham-fisted ham-fisted approximation, but it does work up to a point. It's still better than the Euler-Maruyama method at moderate time steps. However, as the time step goes down, the Euler-Maruyama method winds up becoming better. So as of this point, I can say that the one new method that I've come up with has failed, and I am still looking for newer methods, something that is more reliable. However, this is still a work in progress, and there is still lots to look at. I am drawing my inspiration from techniques from mathematical finance to look at the Bessel process, and I am trying right now to expand that to the multivariate setting. Hopefully, we will get a better method than the Euler-Maruyama method in terms of convergence, but better than the Averin-Artemiev method in terms of computing time. With this, I would like to finish my talk. Thank you so very much for listening. If you want to ask me questions verbally, well, I'm open for questions, of course, or if you cannot, then please use the QR code over here to send them via text.
Well, I had a question if there if is there any difference in the memory requirements for each of the methods?
Oh, indeed, there is a large difference in memory requirements. So as I mentioned before, this method, the Averin-Artemiev method, requires a matrix inversion, which means that you need to store these matrices and you need buffer space as well to do Gaussian, what's the name? Gauss-Jordan reductions. So you will need maybe 2n squared times the amount of memory that you would need with the Euler-Maruyama method. So yes, it's not just costly in terms of time, but it's also costly in terms of memory.
Okay, thank you.
Okay, Gabriel. I have one more question.
Thank you, Sergio, for the talk. I was wondering, in maybe you could put the slide that was previously when of your method.
You mean the one that failed, or the one before?
That, since you have to, no, the previous one.
Oh,
Since you
this
have
one.
to invert the Hessian, the matrix that is costly, but what if one expand this to order dt and take only the
Yes.
so up to order delta t square maybe, or?
Well, yes, you can do that. And indeed, I tried to do this, but that approximation assumes that that the spectrum of this matrix is always smaller than 1, that all the eigenvalues of this matrix are always smaller than 1, and that does not that isn't valid when you have a situation where two particles in the Dyson model are close together. In that case, this object blows up and the approximation is no longer valid. So in the end, you wind up having something in that is more or less as accurate as the Euler-Maruyama method. You don't get a significant bump in performance. So there, I'm thinking that probably the right idea is to find a proper approximation of this matrix that can be easily invertible, and that probably is the best way to go. But I'm still looking into it.
Okay, thank you.
So let's take again the speaker.
Thank you very much.
Thank you. Continue with the program. We have the talk by Carlos Alvarez.
Okay.
Carlos, can you hear us?
Right. I can hear you very faintly, but I can. Do you hear me?
Yes, we can.
Okay. Okay. Thank you. So I will.
Okay. Do you want to start sharing your screen?
Yes. So let me just no share. Okay, so do you see my screen here?
It's not coming yet.
Okay. Not yet?
No. Maybe you can try to turn off your camera because we have like a very.
Okay. Okay. Yeah, I will do that. So let me just turn off my camera, and I will try to share again screen. So, okay, it says here that I'm sharing. Let's see here, let's wait. Okay. Not sharing still. Okay, what happens here? Oh boy. And
Again, because we are getting a message that says that you can't share.
okay, let me just stop then. See what happens here. I'm trying to share my screen and you can display, share.
Okay,
I will try to share my entire screen. Let's see if it works. Oh boy. Not yet. Not yet, right? What's happening here? Oh boy. Okay, it's not, I don't know what's happening here. Somehow, for some reason, it's not sharing. Let me just try it one last time here. I don't know what's happening. Okay, so share the entire screen, let's say. Okay. Okay, so I'm waiting. So do you see something there which I'm not seeing here, maybe? I will try to share again the tab, the presentation. Window, yeah, this one. Share, please. Okay.
Okay, now.
Oh,
Business.
okay.
Just go to the first slide, please, and then I do the. Okay, thank you. So
Thank
now,
you.
finally.
Finally, thank you.
Uh,
Okay, so I will start.
we have one particle engine with a porous piston talk by Carlos Alvarez. So, Carlos, the floor is yours. You have
Thank you.
15 minutes.
Yes, thank you. So thank you first to Daniel and Gabriel for inviting me to the workshop to give this talk. It's an honor. So my name is Carlos Alvarez, and I did this work along with Professor Manuel Camargo, Professor Gabriel Telles. So I will start with the presentation. So first, let me introduce a system which is the base of our model here, which is called Sirot's engine. So you might have heard about this system before, but I will explain it very quickly anyhow. So the idea is that we have a container. We have a container which is in contact with a thermal bath at temperature T. And there's a single particle inside this container. So we will call this as one particle gas. And the idea is that this particle is just bouncing there, extracting energy from the heat bath. So Sirot's idea was to introduce a piston into the container, in the middle of the container, so that you create a pressure difference between the part of the engine that contains the particle and the part of the engine that does, or the container that doesn't contain the particle. So the particle will just push the piston to one side. And if this happens, then why not hanging, for example, a mass from this piston so that you can get work done, so that you can perform work. In this way, you will be able to lift the mass here. And up to this point, you will think that this violates the second law of thermodynamics because we are doing work and we are connected to a single heat bath. But there's a catch here. And the thing is that when you want to continue doing work, you have to put a new mass. And more importantly, you have to remove the piston and put it in the middle of the container again. The thing with this is that once you do this, you don't know if the particle will end up in the right side or in the left side of the engine. And this is important because the mass has to be hanged from the same side as the particle if you want to be able to lift it. So later, it was found that to do this, you have to measure the position of the particle and you have to store this information in some kind of memory so that you can use this information later to know from which side to hand the particle. This process of erasing the memory, which is called now Landauer principle, says that this erasure will cost you kV logarithm of 2 entropy increase. So the energy lost will be kVt logarithm of 2, which is the same energy that you obtain by lifting the mass. So you offset this gain, and this does not violate the second law of thermodynamics. So our idea was to say, okay, what if we can make some small modification to this model so that we avoid having to remove and insert the piston again. So we did this small modification, and it was to punch a hole into the piston, let's say a small hole, so that the piston, the particles, sorry, most of the time will hit the piston, pushing it to the opposite side, but with some probability P, which we will call the porosity, the particle may traverse to the other side of the piston to push it in the other way. So a regular cycle will look like this. First, we have the piston, and we have hang the mass because we want to perform work. And the particle will push the piston up to the other side. At some point, in the same way as for Sirot's engine, we will remove the mass that has been lifted and now has a high potential energy and replace it with a new, fresh, low potential energy mass. And sometime after, the particle might cross over the pore and push the piston to the other side. And if we have a mass also on this side, we can continue to perform work in this way. The difference here is that we are not measuring the position of the particle. But instead, we have to perform a feedback control on the system, which I will explain in a moment. So the idea here of the feedback is that we will have a parameter lambda, which might have 3 values, which I will explain. So L for lambda means that the piston has a mass hanging from the left side. R means that there is a mass hanging from the right side of the piston, and U means that the piston is unloaded, so that there is no mass hanging from it, okay? So the protocol goes as follows. If the piston is located in any place, first, so the positions at which we will free the old mass and connect a new mass, we will call A and B, okay? So when piston arrives to A, if there's a mass hanging from it, we'll remove it. And once the piston gets to this position B, we will hang a new mass from it. Okay, so the protocol says that if the piston is in a position which is not B or A, then the state of lambda will remain the same. And once the piston gets to, let's say, the left side, here in A, if there's a mass hanging from it, we will remove it. So lambda will go from being R to being U, or in the mirror case, when it goes to the right side, then we will go from L to U. And once the piston gets to the second position B, then if the piston is unloaded, then we will attach mass to it, and then it will become L or R, depending on if it is on the right side or on the left side. So this is a feedback control that is performed by some external agent. Okay. So now let me show you about some simulations we did with this toy model. So here we have the trajectory of a particular realization of the system. So in the upper panel, I have a position in the vertical axis versus the time on the horizontal axis. And the black line is the trajectory of the piston. So we can see here that the piston is on the right side. So it's bouncing there against the edge of the box. And the green line is the trajectory of the particle. So we see that the particle is hitting the piston. And every now and then it crosses to the other side. For example, two examples of these events are signaled here by this red arrow. So here the piston, the particle is crossing to the other side of the piston. And there are many instances of this here, but here there's another one of these instances. So we see that at some point, the particle is able to transfer enough energy to the piston so that it takes it from one side, let's say the right side, to the left side, okay? And then the piston will remain at the left side until the particle crosses and is able to push it again in the opposite direction. And that's how the cycles go with this small engine. In the lower panel, we can see still the trajectory of the piston, but then we have two new trajectories, which are those of the hooks of the masses. So remember that the masses hang from the piston and they are connected with a hook that collides elastically with the piston. And these lines, the blue and red lines, are these the trajectories of these hooks, let's say. So we see here that we have a hook hanging from the right side and it bounces against the piston until the piston is able to get to the opposite side, to the left side, and then we remove the blue, let's say the blue mass, and we hang a new red one there. And then the red one will be there until there's enough energy for the particle and the piston to lift it completely and go to the right side, and then the cycle repeats. So this is how it works. And we can plot here the work performed by the engine and also the heat that's consumed by the engine as a function of time. So on the left panel, we have a single realization, a single experiment, single simulation. And on the right side, we have, I think, the average of 150 realizations of this experiment. So we see that indeed the engine is able to perform work, which is the black line here. So the slope would be the power output. And on the blue line, we see the consumption of the rate at which heat is being is getting into the engine. And we see that the slope of the heat one is in magnitude is greater than that of the power output, which means that the efficiency should be less than 1. So there's no worry here that we are violating the second law of thermodynamics. And so speaking of efficiency, of course, we want to compute somehow this efficiency. And in this case, because we are in a mesoscopic regime, very small systems, we will compute the stochastic efficiency, which is defined as the ratio between the power output and the income energy heat rate. And we do this over a period of time, t, so a window of time. We take a window of time of length p, and during this window of time, we compute the efficiency. And we can do this for many realizations, and from these realizations, we obtain a distribution of the stochastic efficiency, which is this P here. Now, the actual way to compute the macroscopic efficiency from stochastic thermodynamics is to estimate what they call the large deviation function, which is shown here. And this function consists in taking this distribution of the stochastic efficiency and taking out the logarithm and divide by the t, which is the time period over which you are performing these measurements. And then let this time, the window length, tend to infinity. So we, of course, tried, we did this. First, we computed the distribution of the efficiency. So here we have the efficiency values on horizontal axis, and then the probability of finding these values on the vertical axis. So this is the distribution, sorry. And we see here that we are changing now the time window over which we make the measurements. The red one is a time window which is equivalent, or is the same size of Tc. And Tc is the period of time, the amount of time that transcurs between the moment in which new mass is loaded to the system and the moment at which a mass is with high potential energy is removed from the system, which we will call the cycle, like the period of the cycle of this engine. So we see that as the T increases, the distribution becomes more narrow. And with these distributions, we try to estimate the large deviation function. So we compute minus the logarithm of this distribution over t, and then we do this for values of t that increase. Okay. What's interesting here, what's important here is to check at the minimum of this large deviation function, because the minimum will signal the macroscopic efficiency of the system. So we see that the curves here, as t becomes larger and larger, have a minimum which moves here. So in the inset, we can see more clearly that at this point, when we are about using a t of about 320 times the cycle period, let's say, we can estimate a macroscopic efficiency of about 0.82, let's say. So here we plot this efficiency as a function of P, so the value of the porosity or the probability for the particle to cross to the other side of the piston. So let's focus here on the red line. I will direct your attention to red line, where we have the efficiency calculated as shown earlier, and we see that as P increases, so as the probability for the particle to cross becomes higher, then the efficiency also increases. But now I will direct your attention to the black curve, which is the power output. But as the efficiency increases, also the power output decreases and tends to 0. And this is because when the probability is really high, then most of the time the piston will be just jiggling left and right without doing any real work. So that's it. So we have that this engine is able to perform work with some efficiency. So we have here some power output, but there's still some missing element here, and that is that we are performing this feedback protocol. And this feedback protocol, no doubt, consumes some energy. And in this study, we don't have any measure for the amount of energy that this protocol is consuming. So this is missing from the efficiency. It would be important to know for the efficiency. So there are two ways in which we could extend this work. So either we find out a way of computing the energy that you have to invest in the feedback control protocol, or we try to use a system without feedback control and see what amount of work we are able to produce with that. So with that, I'm on my time now, so I want to thank you, and I'm just open for any questions that you might have. Thank you.
No? Okay.
Yeah, I can hear you. Okay.
There is one.
Okay.
Yes, Carlos. Thank you for your talk. That's super interesting. I was thinking about the first talk of the day by Behofer, where he has an experimental realization of Maxwell's demon, right? I was wondering if you have any ideas on how an experimentalist would go about realizing your model experimentally.
Yeah, no, actually, I don't have any idea because I'm not an experimentalist, but I would imagine that you need to have first a really small system, so a nanoscale maybe system, and then you have to isolate a particle within a container, yeah? So I don't know how this would be possible. I mean, but this is just because I'm not experimentalist. Maybe someone with this kind of knowledge can have a better idea. But at the moment, it's true that this is just an ideal model as Szilard's engine was, and I don't have a very good idea how to realize it experimentally. Yeah, sorry.
Thank you.
Yeah, thank you.
Yeah, we have one more question.
Yeah.
Yeah, maybe just a comment on the last comment that one configuration that one might think of is the double well potential where you could move the barrier. Sorry, I'm waving my hands in a way that you guys can't see, but if the barrier can be moved and has a finite height, that I guess hopping over would be kind of like a hole in the barrier. And so maybe there's something like that would work.
Yeah, agreed. So maybe also some tunneling probability there could act as a whole. Yeah, agreed. Yeah, that might be a way of doing it. Yeah, thank you.
Okay, so that's all. So let's take a speaker again.
Thank you.
Now we move to the last part of the session. We have a program. So we moved the John Freddy Mateo's talk to.
Yeah.
So go ahead. You have anything set up?
Let me show the presentation and we can start. Ya, ahí está.
UNAL 2. UNAL 2. Entonces, comparte la pues, entonces ya compartir. Ah, está.
de la reunión.
O sea, lo tienes que hacer explícitamente con
Me sale unirme o presentar.
No, no te sale.
Ajá. Mira. Le doy aquí o aquí.
Permite que. Ah, es que de pronto es permiso, ¿no? Permite.
No, sí, ya.
Ah, ok. Ah, entonces,
Aquí.
presentar. Permite dejar de compartir. Estás usando el modo complemento. No, pero ahí no es. No,
Bueno, entonces sí, no, aquí está.
aquí está. Me parece bien.
¿Dónde puedo conectar esto?
Ah, ahí está.
Mm.
Pues entonces espérate un momentito. Tienes,
¿Cuál es?
tienes toda la pantalla, espera acá.
No, ahí no blanca. Esta no. About no fusion and fusion process in Dyson gas. Let me show. This is the order of presentation. Fits. Let me introduce the work model, then talk about regime of determinalization, and finally, I talk about dynamics in the fusion regime. We are working in a two-dimensional system. we have a thermal bath with temperature T and drag coefficient F. In this bath, we can put randomly positioning some particles, say n charged particles, with the property that all particles in the system have the same charge. Okay, therefore, there is a electrical repulsion between the charge in the system. For consistency of the electrical repulsion of the system, we have to use a background potential to retain the particles in the bath, and use the approach of Langevin equation to have into account a stochastic force for the particles in the system. The equation of motion, therefore, is the Langevin equation, and here is the draft in the system, the electric force, and the stochastic force in the system. The stochastic force is habitual. We use a noise, a Gaussian noise with mean value 0 and no correlating time noise. To find the electric force between the particles, we need to solve in the Poisson equation in 2 dimensions, and we have a setting r equals 1. R is the radius of the circle, and solving this equation, we have electric potential in logarithmic form. This is with this we can find the force between particles in the system. After some calculus and working in the overdampened regime, we have this equation that models the change of position for each particle in the system due to the electrical interaction and stochastic force in the system. This is the condition of our Gaussian noise, see? And then we can simulate the behavior of the system. Here are our simulation parameter. We have used a parameter beta. This is which is the radio in between change of the particles and bath temperature, and time steps for the simulation given by this equation. This equation can be obtained. Calculate this for the position of the particles, and we have used 100 particles, all with initial charge equals to unity. In this simulation, we can see some features of the system. First, as increasing beta in the system, the particles can move quickly or not. And some important thing in this simulation is that the position of the charge are changing in time, and we can ask for the distance between particles, how are distributed this distance in the system for each value of beta and in the time evolution. Please, next slide. Well, if we can, another important thing is that initially the particles are uniformly distributed in the domain. So the dynamics start with this uniform distribution, and we can measure the distance in the system. These plots are made for 1,000 simulation of the system. The before plot showing one of the simulation. Here we can see the change in time of the first distance distribution between the system, particles of the system, and we can note that this behavior for later times can be modeled using the Viernes surmise, which is the Wigner conjecture of the distance between particles. Here we can see this distribution plot for different values of C. Beta in this case is the usual beta for the Gaussian ensembles. So the system has a relaxation to this distribution, and this is the behavior. So one can asking the before plots if we fit with this model and using the conditions of the distribution, which is this distribution must be normalized and the average value of S must be equals to 1, we can choose the fitting parameter B, and for parameters A and C will be functions of B, explicitly gamma functions of B. Please, next. Okay, after make the fittings using the Viernes-Surmise model, we can see in this plot the behavior of the B parameter of the fitting changing in time for different values of beta. So here are two important things. First, we can see that the system in time evolution to a equilibrium state here. And second, this equilibrium state is governed by the beta value, Gaussian ensembles, fixed beta equals 1, 2, and 4. However, we can see that this behavior is valid for different values of beta. Next thing that we can do is plot the dispersion of the system, measuring with the sigma standard deviation of the position of the particles, and we can see how this evolves in time. So here we can find that if we choose a right scale on time and sigma, like this, we can get a functional form that doesn't depend on beta and the other parameters of the system. And we can see that the time scale follows a rule like this. Here's tau, it's the same that t here, so tau is the log t. However, here in this plot, the log t is in the axis scale, so t is the time value. Here, tau is the log t of these point times. So after analysis of these parameters, here, we can find the behavior of 3 of the parameters. This 4 parameter is unknown today. So we can relate these scales with these parameters to show the scale behavior of the system. Well, if you note in the simulations, if you note in the distance distribution, we can ask, despite of the electrical repulsion of the particles in the system, these particles can be very close together. So we can analyze a regime, a new regime, where if 2 charges are very close, they can be merged, forming a single one particle. With the particle has, the final particle after reaction has the sum of the charge of the 2 particles that we meet. Okay? So this is the picture of this process fusion. 2 particles can be very close. This is the critical zone, that if two of these charges are in this zone, can be merged into a single one. So we can define a critical fusion angle, which is controlled by this parameter LF, that this parameter allows to use scale this fusion zone. Here is another simulation. This one simulation, we can make 1,000 of this simulation. And here we can note that first, with beta, the charge per particle grows, like see. The size of the points are not the size of the particle, it's the size of the charge. And second, the number of particles can change in time. For beta, this number of particles in the system change in time, and therefore there are performing clusters of great charge with beta is less than 1. For beta greater than 1, the number of maximum charge created in the system is lower. So the number of particles don't decrease so much compared with this value. Please. Okay. What happened in the system? If we plot the time evolution of the diff before, we can see that initially all the particles has the same charge. This is for beta equals 0.1. And initially randomly distribution, some particles are very close, so they are in the zone. They can be merged, therefore. And here, the clusters of size, the charge size 2 are created, so the clusters of charge 1 decrease. Next, can start performing charge of particles of charge 3. There exists in the system particle charge of size 2. This is the particle charge of size 1. This decrease, this increase. Here, the particles of size 2 in charge reach a maximum value. Then in time, it starts performing particles of charge 4, and so on, and so on, and so on. This is the reaction. There is a moment in time where the particles of size 1 they not exist anymore. So, however, more particles are created in the system. Okay. What happened when we change beta? First of all, for betas lower than 1, we can see many clusters are created. Here we have the creation of the clusters of size 1, 2, 3, so on until 12. However, for beta greater than 1, there are lower clusters created in the system. Here, the black line is the total number of particles in the system. So there is an interesting behavior, because for betas, here not show that, but for beta greater than 1, the plots change in form, appearing zones of different concavities. So this is very interesting to study. However, first of all, we interesting to know how is these time points when the cluster size start to appear. So in this direction, we can plot the start time for the initial creation clusters and the time to reach the max value. We can find these roles of governing these dynamics. That means the time to starting the creation of the clusters and the clusters reach to maximum value follows the same roles. It's obvious that these values change numerically, but the rule is the same for these time values. And finally, if we can asking for the maximum population that each species of clusters can be reached, we have this relation. So the maximum population goes in this form, depending potential in the potential in a low potential of parameter D that can be found in this manner. So the maximum population follows that rule. Some conclusions to ending this presentation. The thermalization dynamics, it's valid, show the validity of the binary spacing distribution for other beta than the usually in the Gaussian ensembles. There is a scale time for these dynamics. On the contrary, in the fusion dynamics, we have these calls for the start time and the maximum population in the system. Thank you.
Thank you. Go ahead.
Thank you. This talk was super interesting. Thank you very much. One thing that I want to ask is in slide number 5, you have your spacing distributions and you were fitting them with the Wigner-Sermis, correct?
Right.
I wanted to know for beta equals 0.1, how did the parameter b look like? As in, the parameter b, the large b, I think it was that you had in your slide. It should coincide with the beta, if I'm not mistaken. Does it coincide? Are they the same? So b of beta, does it turn out to be the same thing, or is there something different there? I think it's two slides before. This one, yes. Here you have
this parameter.
Yes, on the top left you have s to the power b. That large b should be the same as beta in your model. Do the two have the same value in the end?
Well, in this case, this is the reason for which I show this plot, especially for beta 0.1. In this zone, beta b parameter of the fitting is nearly to beta 0.1. However, for this parameter, the dynamics of the system is highly related near to free diffusion, is pseudo free diffusion. So take values in this zone to testing this dependence of S in the potential B, in the power B. It's very complex before the delta T usage, so the simulation is very sensitive to this value. So this is the reason for in this zone, if you can see it, you cannot, there are many points.
Yes.
We need to refine the resolution for this histogram. However, for this, you can see that not the accumulation points in the zone. This is the problem has had this beta parameter. For beta equals 0.3, 0.4, this problem not appears with beta near to 0. And this is the reason for this b value and beta value are near, but not exactly the same.
I see. Because so one thing that is very well known is that two particles in a Dyson model, be it circular or linear, they will not meet provided beta is larger than 1. So in that case, the Langevin integration when beta is less than 1 gets a bit dangerous, numerically speaking. When two particles get very close together, the numerical integration winds up showing signs of instability. So I was wondering if you had gotten the correct results, but you mentioned that they're not exactly the same. So I think that then your assessment of the situation is correct. That was one question. I had another question, which was for large beta, you still had clustering. You still had particle aggregations, yes?
Yes.
So my question is, do you have a critical distance at which aggregation doesn't happen anymore for large beta? Because at large beta, clearly particles don't ever touch each other. So I would assume that eventually, if you choose your parameter L, was it small enough, you wouldn't have any aggregation. Can you comment on that?
Right. For this time until now, we testing the simulations for beta equals 4.0.
Mhm.
For betas greater than this value, the computation time is very large. Okay,
Oh,
so we can note there is that here is only for the beta values. We have a 0.01, 0.1, 0.2, so on, until beta 0.4 in steps of size 0.2. So we
mhm.
can note that evidently clusters appear in a very lower scale. What I mean, uh, minus population.
Uh-huh.
Okay, so for this value that we can analyze, um, there is a markedly transition, and this is the plot, the curves of the aggregation of clusters. However, for values of beta greater than 4, the time simulation is very large. So we have to include in the algorithm of the simulation uh, backup of the final data. Uh,
Ah, to
in
run the simulation and continue it
which
later. Okay. Over
uh,
several runs. I
uh-huh,
understand.
yeah. To work in the future, testing more large times and probably betas, values of beta more larger than 4.0, 4.0, yeah.
Hmm. Thank you.
Okay, thank you. More questions?
So, more questions here in the room? Just a quick one.
I just would like to know what the beta parameter there is the coping parameter between the particles. Okay, so for which parameter you obtain the Gaussian orthogonal ensemble and the unitary ensemble of the matrix?
Okay, for beta equals to 1, we have the Gaussian orthogonal ensemble. That is the blue curve. For beta equals 2, we have the Gaussian unitary ensemble. And for beta equals 4, we have the Gaussian symplectic ensemble. Right? In this plot, we can see the variation of this distribution if we can vary the C parameter.
And why is not possible to do the simulation for beta and this go to infinite?
Essentially, gross beta has implies a large chain computation because the dynamics here is very slowly evolution.
And you don't have there a sort of one-dimensional crystal?
This is working in this model only because there are many parameters to testing. We can change if we wish the number of particles.
Okay.
Addition to this, we can change the initial distribution of the particles. We can use here a initial uniform distribution. We can use Poisson distribution, Gaussian distribution, or if we wish, we can use this distribution and see what happens.
Okay, nice. Thanks.
Thank you.
Thank you very much.
Thank you.
Thank you.
Thank you.
We only have 15 minutes or so for the break. So, go on, Rob.
Gracias. Merci.
Yo quiero enseñar esto, pero sigo yo hablando.
Ah, listo. Perfecto.
No. Ahí está, ahí está, ahí está.
Okay, well, welcome to the second session of this morning. So we are going to start with Juan Gabriel Ramirez, which is from the Universidad de los Andes, and we'll talk about the physical properties driven by phase separation in electron correlated materials, percolation and avalanches.
Okay, thank you very much for the invitation. I'm going to try to show a lot of experimental results that I hope that they can convey the idea that percolation and avalanches are important and useful for different applications. So I hope that I'm going to have enough time. I have a lot of slides, I already know. So if, Gabriel, if you have to, just let me know when I should stop, because I probably will not make it up on time, okay? So the first thing that I'm going to try to do is to show two materials that they display this phase separation, avalanches, percolation, in general, phase transitions. So, and I choose vanadium oxides, V2O3, and this is a manganite system. It's a kind of a complex material. It's a combination of lanthanum, praseodymium, calcium, manganese oxides. With those two, I'm going to try to show my results. This is the group, by the way. So if you want to look for more information about what we are doing currently, please go to the site. And then, okay, so let's start. Okay, so, oops, wait. Okay, so I'm going to introduce briefly what is the idea of hybrid materials, or these kind of materials that we have here. I'm going to show some dynamics here in these type of materials. By dynamics, I mean either transfer properties or magnetization properties. And then I'm going to talk about this manganite system that we have here. Okay, so then first of all, I want to explain what is the idea of a correlated material. That's probably for the audience is maybe not well known. So the best example that I can give you is that in a normal material, you have of the order of 10 to the 23 atoms. So the most of the physics that we have, the ones that we use in the computers, those materials that they work there, the physics of them are mostly calculated using a 1 electron approximation. But if you have to account for all the electrons that they interact, then this problem will be almost impossible to solve. And this is actually the idea of electron correlated materials. So let's think about an ideal system. So in an ideal system, like in the one that I just described, that I can think about just one single electron, is something like this. So you have a highway where there is this cars that they are moving, and then they are far away between each other, and then they don't interact. So if one car stops here, so nothing happens to the other ones around. So that's kind of the idea of what an ideal gas is. There is the extreme, which is a extreme correlated materials where you have a bunch of cars together, and those cars also, I mean, moving around there is very complex. It's almost impossible. If you want to stop, I mean, you are practically stopping all the time. And then, so here there is kind of a lot of interactions. And this is, by the way, this isn't in China, but could be Bogota most of the time. And then, so here we say that we have local interactions, or which causes long range effects, okay? But then what I want to try to show today is that the physics that I'm interested on is something in between, where you have a highway with a bunch of cars, not too much, and they move very fast. And this is the fact that a car will stop here will propagate very fast. So if a car stops in a highway, so it will cause a disaster. And then this is what we call correlated materials. Propagations can propagate through the systems, and then any perturbation that happens in this will be easy to detect. Okay, and that's the system we are working on. So these correlations between electrons in those systems can show up as the dependence of the disorder. Disorder meaning that something that we do into the system, and then that effect will propagate through the whole sample. Okay, so we will study these degrees of correlation. Okay, so back to the materials. So I'm going to show you a bunch of examples where we actually see these correlation effects. And here we have one of our first results where we show that this particular system, vanadium oxide, this is a thin film grow in a substrate. It has 100 nanometers thickness, and we built a device, something like this. So here, what is here in between is the vanadium oxide film, and then you measure, for this case, the resistance of the sample as a function of temperature. And then what you get is something like here, I'm showing in this inset, and I'm probably going to borrow this stick again, which is probably a good idea. So this is the resistance as a function of temperature, and then what you don't expect is that the resistance do this. So it basically goes from something to 10 to the 5 ohms to something to less than 100 ohms. And this is a huge change in resistance, and the only way that we can explain that is by those electron correlated electrons that belongs to this vanadium oxide material. But inside here, you see there is some features, and then if you zoom out, it's actually what I'm trying to plot here. So these are jumps that occurs into the resistance of this particular sample. Those jumps change in size depending on the size of the electrode. If the jumps are smaller, the jump, if the gap here is smaller, the jumps here are bigger, okay? And this is an effect of those percolation effects that I talk about. Basically, the idea is that you have a threshold here where the sample becomes fully metallic, and the reason why this goes from insulating to metallic is because there is a metal insulator transition. So here the sample behaves as a metal, as an insulator. Here it behaves as a metal, and in between you have a network of regions where the sample behaves as either metal or insulating. And we can see that by actually looking at the domains. Well, I'm going to show that here. This is also concomitant with the structural phase transition. Here you have a monoclinic structure, and then here you have a rutile structure. So structural phase transition at the same time. So we did some histograms of these jumps, and what we found is a power law, meaning that there is no well-defined scale for the jumps. So, so this is some sort of a fractal behavior. And then what we found is that this alpha also, it's material dependent. So our claim is that this alpha actually shows some or will display some physical properties of the material, meaning that if the correlations are stronger, then this alpha will actually be somehow different. And that's the idea, and this is how the whole story started for us. So this is a map where the technique here is some type of a microscope. It's called SNOME. And then what you do is that you scan in the surface of the sample, and then you probe locally what is if the sample is a metallic or an insulator. This is work done by Muntas. At the time was a collaborator of us. And then the idea here is that as you cross the transition, you see these puddles or these domains that grow into the sample. So basically here, if you measure the resistance, if you imagine measuring the resistance between this point and this point, here you have a precorrelation threshold, you have a path that connects these two electrodes. And that's the idea of the big jump that we just saw before. So, so we wanted to know what is the dynamics of this. So we wanted to kind of look into this and to study how these domains nucleate, how do they propagate, what is the dynamics of them, and then if this is, and if we can extract from them some sort of information about the percolation process or the interactions. So we did that, but with a different system. It's a kind of a brother of vanadium oxide, is a V2O3. So it's more or less the same. I'm going to show you some differences, but this material also has as you see here, it has a metal to insulator transition. Here's a metallic. Here is a insulating material. The transition is at lower temperature, so it's 150 Kelvin more or less. And then at the same time, with this electronic transition, you have a structural phase transition here. This is an X-ray diffraction pattern as a function of temperature, and you see that one of these peaks shifts to higher angles as you increase the temperature. So this is a signature of a structural phase transition. This is a signature of a metal insulator transition. In addition to this system is antiferromagnetic at low temperature, and at high temperature is paramagnetic, which is just make things more complicated. But anyhow, so the idea here is that we make some devices again in these samples. So the devices here also change in size, and here in between you have the V2O3 material here. So the idea is that we studied the jumps again, and then we saw the jumps distribution as a function of temperature. You see that they are kind of more or less clustered around the transition temperature, which makes sense. And then we did some statistics of the jumps. All of them show power laws, and then we calculate the alpha, and then as you can see here, the exponents for the cooling and heating are somehow slightly different. We didn't go into the details to kind of to prove if there is a difference between going into high temperature and low temperature, but that's something that we will investigate later. But the bottom line here is that the exponents, which I told you may give information about the interactions, they are slightly higher than VO2, okay? And then if we compare these two things here, I'm comparing here VO2 and V2O3, you see that V2O3 exponents are consistently higher at higher sizes, okay? So that is kind of interesting because there is always a discussion in people that work in these kind of materials if there is, because the nature of the transition in VO2 and V2O3 is different. So V2O3 is a mode insulator, or people believe it's a mode insulator, and VO2 people think that it's a Peierls driven insulator. So the physics between these two is completely different. And then here we show that by just looking at the statistics of the distribution of the jumps, that might be like a way to prove it, actually. So that there is more interaction in a mode insulator than in a Peierls. That makes sense for us. So, by the way, we compare this with just like a random percolation model, just by assuming that everything that switches randomly. And then those are the black points here. And you see that those are closer to VO2, which means that that particular system might be just like, I mean, whatever the interaction is more close to just a random process, which is not the case for V2O3. And that's one kind of idea. But we also wanted to study the spatial distribution of those domains, okay? So then we went to one of our collaborators and then asked them to help us to actually measure those domains with the same microscope. This is the SNOM, the scattering near field infrared microscope. And here you see that we were able to measure the resistance as a function of temperature inside the microscope, okay? So here, whatever is blue, it means that it's insulating, and then whatever is red means that it's metallic. And what we found is this. So as you cross the transition, you see that there is a phases growing here. You have this kind of region where it's mostly metallic according to the technique, and then it grows, percolates and grows, and then at the end it becomes red completely, which means that the sample goes from insulating to metallic. And that's by itself nothing kind of spectacular because this is what we expect from these measurements. But if you want to see something spectacular, then you have to look into the details of how these domains grow or how they behave, okay? And that's what we did. So this is the same kind of images, but just with a smaller magnification. And then you see that there is some patterns that form, like a chess table. And then, so what we look at this was the size of the domains, the perimeter of the domains, and all this kind of stuff that you can do with the images, okay? So what we find is the following. So if you look into the distribution of colors, meaning colors here, the phase of insulating or the metallic phase, and then you somehow compare the same distribution but with the resistance, okay? So if you take the resistance as a function of temperature, I'm showing here, and then you calculate the derivative of this curve, and then you put the two things together, then you see that the percolation threshold that happens in the sample coincides with exactly the distribution of sizes in the images, which is kind of interesting because it means that this particular point here is connected to the microstructure of the sample, okay? Meaning that it's connected to wherever the sample is causing these domains to grow. And the other thing that is kind of interesting is that these domains have some particular direction. So in this case, they rotate 60 degrees. And this is actually connected to the way that the structural phase transitions occur. Turns out that you are going here from something that is rhombohedral, like a honeycomb lattice in a way, to something that is monoclinic. And the only way to go to this, at some point, the structure have to choose one of the 6 possible ways to create like the honeycomb structure. So that gives you the 60 degrees here. So basically what I'm saying is that the domains rotate just to accommodate the rhombohedral structure. Then the question is, this is from the physics point of view, or the fundamental point of view, very interesting, but we wanted to use this as a way to induce some properties in a material that is next to it, okay? Because here we have a structural phase transition. This structural phase transition can induce a strain in some material that is next to it. That was the idea. So what we did was we grow a V2O3 film. In top of it, we grow a nickel film, which is a ferromagnet, a typical ferromagnet, and it's very soft. It means that if I stress or compress the nickel, it will change, okay? And then we study the magnetic properties of this material, this hybrid, okay? And then what we did was just to measure hysteresis curve as a function of temperature, nothing spectacular again, but we noticed that there is a huge change in coercivity. If you plot this coercivity as a function of temperature, then you get something like this. So this is just as a reference, this is the nickel just by itself. So it's just nickel grow into a sapphire substrate as a reference, okay? So the nickel should not show any kind of strange behavior. Instead, the V2O3 nickel film, this hybrid material, shows this huge peak. It's almost 300% change in coercivity field. And then this might not be, might not look like something useful, but if there is something called some memories that work with the magnetic properties induced by temperature. So you can think that if this will be like a memory element, a magnetic memory element, you can actually go from here to here by hitting with a laser and then be able to grow information here and then cool down and then have like that particular bit just safe because the coercivity now is bigger. And that is the idea for the high temperature magnetic memory devices, okay? And we actually filed a patent with this result. Okay, so I wanted to connect this somehow with the microstructure of the magnetic of the magnetism of the sample. So we did some simulations here. So this is micromagnetic simulations with a program called UNF. And then what you do is that you imagine a sample with just regular domains. Then you start putting here just nucleating domains of the other phase with an interface between them. So you have the high temperature phase, the low temperature phase here, and then you have something in between. Because we thought, okay, so if there is a gradient of strain, it should be something that connects the two extreme phases. So it should be some kind of regions that because the strain has to be, I mean, the lattice has to be continuous. So this is exactly that region. And turns out that if we do this, we start to nucleate in more domains. Then we see that when we get the percolation phase of this, then we had a maximum of the coercivity field. And then these two things basically coincide with the percolation threshold of what we observe. So this is the magnetism, and this is the images and the transport. So everything is connected. And then with this, how much do I have? Okay, so then just let me just jump to the conclusions. I can show you more, but probably in another conference. Where is it? Where is it? Oh, here. So the bottom line is that we can control the magnetism by using materials with the structural phase transitions. And then we can combine this just to look for this. And then in this particular case, percolation and avalanches are kind of important for driving these properties. Thank you very much. Questions?
Just a short question about the size of these kind of heterostructures. What is the typical size of these?
You mean the sample thing?
Yes, yes.
So the vanadium oxide typically are from 100 to 300 nanometers, and then the nickel on top is typically 10 nanometers. We have done like a systematic study of all different sizes, and all the effects are somehow scaled to the size. So,
okay,
so that's more or less the range.
Okay, and it is necessary to take into account, quantum effects there in order to describe the physics behind these results, or not? I don't know.
You mean quantum effects, or?
Yeah, yes, because if
So
the size is so small in order of the nanometers.
Yeah, that's true. Actually, at some point, we were discussing that just in between, when you have a metallic and insulating phases and you measure resistance, you may have like tunneling of electrons between the smaller, in the smaller insulating regions where it's sandwiched by two metallic domains. And yes, in fact, that's what happens actually. We do have electron tunneling through this. I can show you, I have those results, but in a different system. So it's maybe cheating. But this jumps here, this is voltage as a function of current for another sample, another system. This is the manganite system that I talked at the beginning. And actually we use that fact that we can tunnel electrons through it to build a memory here. The memory mean here being that we can actually set the sample resistance, whatever value we want, either by voltage or field, magnetic field. And this is something we are submitting for publication.
Thank you.
Okay, thank you very much.
Thank you.
Alexandra Perez, co-authors of this work with Brian Rodolfo Barajas and Carlos Jose Paez, we are going to talk to you about an application of this model. Specifically, we are going to show a phase transition analysis in a monolayer of iodine chromide Ca3 using a honeycomb lattice.
The topic we are going to talk today is, first of all, we are going to show you some concepts of our work. Then we are going to talk about microeconomical ensemble. Then we are going to talk about computational model, and finally we are going to give you some conclusions. So the easy model. The easy model is a mathematical physics model which gives us the energy for a system with which have interaction between the particles. So the easy model is characterized by this Hamiltonian, which in the left side we have a exchange constant, the position of the particle A and J, and that gives us the speeds. So the exchange constant is a consequence of quantum interactions like repulsion, localization, dislocalization, and that shows the ferromagnetic or antiferromagnetic behavior. So if J is positive, the material is ferromagnetic, and if J is negative, the material is antiferromagnetic. In the right side, we have the contribution of magnetic field. This contribution have the Bohr magneton, and this is a magnetic moment of a charged particle. In our case, we work with a magnetic field equal to 0. So the Hamiltonian resultant is this. We could have three neighborhoods, but we only consider one. So J is going to be 2.37 millielectron volts. Then the easy model, we could work in 3 dimensions. We can have 1 dimension, but easy proof that in 1 dimension we don't see the phase transition. But in 2 or 3 dimensions we could see this phase transition. So we're going to work in a monolayer of CrA3. So chromium 3 ion. CrA3 is a material which is in a honeycomb lattice and have this electronic configuration to iodine. So 1s2 and ends in 3d5. This is because when chromium gives 3 electrons to iodine, the lastest orbital of iodine is fulfilled. So we could have equivalent system which is characterized by honeycomb, but only the chromium. So having cleared our system, we could know all possible configurations of them. So if we have a system with n particles, we could have 2 power of n possible configurations. And each configuration have 1 energy given by this equation. So we could, with this, we could think in microcanonical ensemble. So our system is isolated. Many of these configurations have the same energy. So we could think in multiplicity. We could think in multiplicity. And we could calculate them, and with this we could calculate the thermodynamic properties of our material. So We have 40 particles, so we have 2 power of 40 possible configurations, and that gives you 1.1 trillion of configurations. And it that have a very high cost, computational cost. So we limit our system to 50 millions of configurations.
Okay, with this theoretical develop, we can implement that in a computational model. So we obtain here energy distribution, the multiplicity, and is the energy. First of all, it's important to see that the range of energy that we obtain from minus 0.06 to 0.04 is very small against the real range that we expect. Why it happens? Because the configurations that we consider are very small against all the possibilities. It's 50 millions against 1 trillion. But even with that, we can observe what is the tendency of the magnetic states. So let's start with that. The most favorable states, as you can see, is an energy that is equal to 0. It's important to see that there is a mean energy. For example, in this state, most of the spins could be up. So in the half, but the another half could be down. So this supports and makes that all the energy of the systems cancels. So we have two contributions. So the mean energy tends to 0. But we can consider another 2 states. First of all, a state of minimum energy or a state of maximum energy. The first state is called a ferromagnetic. Why it happens? Because all the spins are aligned. It's important to take into account that we are in consider a magnetic field. So in this case, without any external contribution, all the spins are in this direction, but the same energy occurs when the spins are in the opposite direction. Why it happens? Can we go to the last? This is in just terms. If all the spins are up, it's always positive. But what happens is all the spins are down, it's positive too. So in this case, the energy is the same. We observe here that the energy of the system has a dependency of the number of particles, the exchange constant, and it is divided over 2. Why it happens? Because you can consider a self-interaction between the spins. If you have a spin I, this spin I doesn't interact with ourselves. It interacts with the near first neighborhoods. And of course, it has to depend of the material. So the exchange, this is the exchange constant. And we can consider now another limit that is the most energy state. This is an antiferromagnetic behavior. What happens in this case? You have one spin up and the first neighbors are down. But if you consider, for example, this spin down, the first neighbors are up. So what's the spin? The opposite. And it indicates that the interaction term that we observe always be negative, so the energy will be positive. So we observe here that the system could have 3 different configurations or magnetic configurations, but the most probable, of course, is a paramagnetic state when they are randomly aligned. And considering the energy distribution, we could calculate some thermodynamic properties. For example, the entropy. We use the statistical definition, the Boltzmann constant, the logarithm of multiplicity, and we obtain this graphic. We observe here that the maximum of the entropy is at the energy equal to 0. Why it happens? It happens because in this state of energy equals 0, the half of the spins are up and the halves are down. So you can obtain a lot of configurations, the maximum number of configurations that fulfills this condition. So the entropy that depends on the multiplicity, the number of configurations, increases a lot. But if we increases or decreases the energy, the entropy starts to decrease. This happens because the number of configurations is very decreased, as we showed in the last distribution of the energy. And finally, we can observe that we can calculate the magnetization. How we calculate that? We subtract the spin up and the spin down variables that we do. This is a random variable, of course, and divided by the number of particles. So we observe an asymmetry against the energy. If we increase the energy, the magnetization starts to reduce. But why it happens? As we have seen, in the lowest energy case, the magnetization is on a ferromagnetic state. So all the spins are aligned. But if you start to increase the energy of the system, the arrangement of the spins are not symmetrical. So it reduce, pass to the paramagnetic states, and ends with the ferromagnetic. It's important to see, again, that the interval could be very large, but with our configurations are considered only as more interval. So we see here that the three graphics that we obtain, the three results are consistent because the magnetization are consistent with the energy distribution.
So the conclusions are, first of all, we could characterize a monolayer of CRA3 with techniques, with statistical mechanics techniques, and using a system with 40 atoms and 50 millions of ensembles. Second, the spin distribution of the system indicates the existence of three states: paramagnetic, ferromagnetic, or antiferromagnetic. The multiplicity of the ferromagnetic and antiferromagnetic states is much lower compared to the paramagnetic states.
Okay, and about the magnetization, we observe the asymmetry that I was talking, the maximum is in energy, and we observe a phase change in the magnetic configuration, passing to ferromagnetic, paramagnetic, and antiferromagnetic states. About the entropy, we observe that the entropy is not symmetrical, of course, but tends to asymmetry of the relationship with the energy. Maybe we suppose that this is because the states that the system could be the minimum and the maximum energy are equally probable. That is aligned in one direction, aligned in another, or one spin with neighborhoods in the opposite, and all that.
Thank you.
Question?
Okay, so I understand the work you did here was theoretical, but is there any experimental results that you can compare your results to?
We didn't find experimental results because the idea of this work was to find phase transitions in other quantities different than the equal, the most common that is the specific heat. But maybe it will be, but in our research, we didn't find experimental verification.
And in this case, you said you had three possible phases.
Yes.
And does that mean that you have also two phase transitions?
Yes, because we are passing into phases.
Okay. And would you happen to have the critical temperatures for the phase transitions?
We tried to find the critical temperature, but the configurations didn't go to. We can cover all the temperatures. So this is because the configurations. We only consider 50 millions of 1 trillion, so we didn't reach. But if we could use those the configurations, we found maybe this behavior.
And one last, why did you choose the type of model that you use to model? Like, I know you use the IC model, but usually you use like Monte Carlo methods to solve it. Why did you choose the microcanonical route?
So do you mean that why are we using this kind of example and not another? Yes?
Yes.
Okay. We tried because in the literature we didn't found that, and we tried to do a system that have no another configurations, because an improvement that we would like to next is to add the magnetic field, so the system is isolated.
Thank you.
Thank you.
Is there another question? I have a question. When you plot the entropy as a function of the energy, there's a region where it decreases. So if you compute the temperature derivative of the SDT, we have a negative temperature. How would you interpret that?
Yes, of course, this happens to in the one-dimensional model. This is like in this part, no? The negative temperature is a system that tries to give energy to the another systems. In this case, it's like a negative temperature is like higher than every positive temperature. In the one-dimensional case, it happens too. But we didn't plot the temperature because the smaller range of temperature of energy that we could obtain with our configurations.
Okay, thank you.
Okay.
Okay, we move to the next talk. The next, yeah. So the next talk is Juan Esteban Bedoya. It's online. So. Yeah. We'll check.
Oh.
Hola. ¿Me oyen? Hola. Disculpen, ¿si me están oyendo o no me oyen?
Yes, okay, Juan Esteban, you can.
Hola, ¿me están oyendo?
Yes, we hear you. Lo oímos bien.
Disculpen, no sé si me están oyendo o no.
No nos está oyendo.
Ok. Supondré que sí me oyen porque escuché por ahí que sí me oían. Y pues bueno, empecemos. Buenos días.
Wait.
Hola. ¿Me oyen? ¿Sí? ¿No?
Can you hear us? Can you hear us?
Hola.
Hola, ¿nos escuchas?
Ok, sí me oyen, listo. Ahora sí, empecemos.
Sí, ya.
Ok, estoy un poco nervioso, es que voy a hacer esto en mi idioma nativo, que es el español, espero no les moleste. Empecemos. Buenos días, mi nombre es Juan Esteban Bedoya Rodríguez, pues como dice el título, hoy voy a hablar de determinación teórica de diagramas de fase utilizando el modelo de Disney y grupos de transformación en campo medio con herramientas de Machine Learning y una simulación Monte Carlo. Como ven, el título es muy grande, es una cosa que abarca mucho, así que como estamos un poco pasados de tiempo, intentemos hacerlo de la forma más óptima posible. Me acompaña en espíritu, porque no está aquí, el profesor León Escobar, que es parte de la Universidad del Valle, igual que yo, y pues empecemos. Primera parte, quiero hablar de una contextualización de los modelos teóricos que vamos a usar. En este caso, vamos a utilizar la aproximación de campo medio y el método de grupos de renormalización. Ambos métodos son conocidos, entonces vamos a pasar por encimita. Vamos a hablar de un par de resultados que obtuvimos utilizando este método, además de una implementación numérica a donde incluimos la parte de Machine Learning. ¿Listo? Empecemos. Si hablamos de modelos cuánticos de spines, existen una gran variedad, como ya hemos visto en todas estas charlas, porque muchas se han tratado de estas. Y por no desentonar con la presentación anterior, hablaremos de modelo de Ising. ¿Por qué elegimos modelo de Ising? En primer lugar, por la misma razón que todos eligen modelo de Ising, simplicidad. Además de que el modelo de Ising, como ya sabemos, le importan únicamente las interacciones con el eje Z del spin. Entonces, como los sistemas los que vamos a trabajar hoy, las interacciones planares decrecen en relevancia, es correcto asumir que este modelo es bueno usarlo. Además de que, como ya dije, aporta simplicidad en todos los cálculos que se hacen. Ahora, la forma básica del campo medio es la que todos conocemos, la que todos hemos visto en pregrado, y es que se parte del hamiltoniano de Ising, usual de toda la vida, solamente que en vez de que cada spin sienta la interacción debido a todos sus vecinos, el spin en general siente una interacción promedio a la que llamamos campo medio. Este campo medio usualmente se modela siendo proporcional a la magnetización del sistema por el número de vecinos o también o 2 veces la dimensión del sistema, dependiendo del sistema particular que estamos utilizando. Y esa constante h, como ya sabemos, es de un campo externo. Para términos de este trabajo, estamos tratando de trabajar con sistemas sin campo externo, por ende, para nosotros h va a ser 0. Ahora, algo muy común que se hace cuando se estudia esto, ya sea en cursos de universidad, es asumir j igual, o sea, j constante. ¿Qué nos quiere decir este j constante? Este j constante nos da una información importante, puesto que este j nos dice que todos los spines interactúan de igual manera entre ellos. Cosa que, pues, como sabemos si tratamos de aleaciones, no funciona. Bueno, para solucionar este modelo, pues todo lo hicimos al menos una vez en nuestras vidas. Se toma la mecánica estadística casual de toda la vida, sacando magnetización promedio por spin, jugando con la función partición, y pues ya, eso es todo. Todos sabemos cómo se soluciona, no tiene mucha mística. Entonces pasemos a la siguiente parte, que son los grupos de renormalización. La idea básica de grupos de renormalización viene de Karanov en 1966. Este concepto nació de la necesidad de simplificar los modelos de interacción entre muchos spines. Por ejemplo, imagínense un grupo de spines demasiado grande, muy grande. Ahora, si es un sistema muy grande y pensemos que hay spines que interactúan diferente, la forma de modelar esto se vuelve un despelote por completo, se vuelve una cosa muy complicada de poder modelar. Karanov vio este problema y pensó, bueno, juguemos así. Separemos por grupos nuestro sistema. Veamos cómo interactúa dentro de los grupos y luego veamos cómo interactúan entre grupos. Así, usando herramientas de mecánica estadística, se simplifica el modelo el problema de un grupo muy grande de spins. Ahora, para utilizar las dos ideas anteriores, se nació este método de grupos de renormalización con campo medio. Primera cosa clave. Imaginémonos un sistema nuevamente muy grande. En ese sistema muy grande, sabemos que no todos los spines interactúan igual. Ahora, tomamos un clúster de tamaño n y un clúster de tamaño n'. ¿Listo? Ahora, como sabemos que su magnetización son funciones homogéneas, porque son funciones de estado, sabemos que entre ambos sistemas la magnetización va a ser proporcional por una constante, en este caso omega, donde omega va a depender del cociente de los tamaños de los sistemas junto con la dimensión del mismo. Dejando esta ecuación 1, pues más o menos cubierta. Ahora, luego, si vamos a la idea de campo medio básico, de campo medio de toda la vida, sabemos que la magnetización es proporcional al campo medio que siente cada spin. Luego, entonces, es natural pensar que si M es proporcional a B y M y M' son proporcionales entre sí, entonces B y B' también son proporcionales. El cálculo no es muy complicado, es una idea muy simple, pero pues funciona. Ahora, ¿por qué podemos usar esto en un sistema real? Primero, sabemos que estamos jugando con sistemas reales, por ende la dimensión es pues 3 y el número de primeros vecinos es razonablemente alto. Para el caso particular vamos a trabajar con 8 primeros vecinos, puesto que los sistemas que vamos a jugar son redes cúbicas centradas en el cuerpo, por ende pues 8 primeros vecinos, y el modelo de Ising, y el campo medio sabemos que sale con mucha lucidez cuando hablamos de dimensiones superiores. Además, también sabemos que cuanto más nos acercamos a la temperatura de transición de fase, los sistemas se pueden reescalar sin cambiar el comportamiento. Muy bien. Siguiendo con la idea que llevábamos, recordemos que vamos a trabajar con la interacción cerca del punto de transición. ¿Qué pasa cerca del punto de transición? El campo medio se hace muy pequeño. ¿Muy pequeño con respecto a qué? A la interacción térmica. Ahora, si tenemos algo muy pequeño que nos encanta hacer a los físicos, nos encanta expandir en Taylor. Entonces, si sacamos expansión para Bs muy pequeños, es fácil ver que este término con este término se nos va, dejando expansión solamente a primer orden, nos queda esta ecuación que nos relaciona las derivadas de las magnetizaciones promedio de los sistemas N y N' respectivamente. Y esto es el núcleo del método, porque encontramos una manera de poder relacionar la magnetización de un sistema con respecto a otro cerca del punto de transición, lo cual nos puede llevar indudablemente a encontrar un punto para la temperatura crítica, puesto que esta ecuación es válida para todo T, en particularmente válida para T igual a la temperatura crítica. Ahora, recordemos que yo les dije que íbamos a hablar de aleaciones. Luego entonces el modelo de Ising, el modelo de ingresar la idea de que podemos tener diferentes tipos de medios configuracionales de la magnetización. Así podemos introducir de manera no tan complicada la idea de que no todos los spines interactúan de la misma manera. Un ejemplo es muy simple. Si tenemos un sistema ferro-para, pues su densidad de probabilidad de enlace sería pues de dos tipos. Pueden haber interacciones. Bueno, sí, pueden haber interacciones de enlaces ferro, interacciones de enlaces paramagnéticos, donde P es la concentración de hierro y Q es la concentración de material paramagnético. Recordemos que la concentración se calcula como lo que tenemos sobre el total, que puede ser una idea rudimentaria de poder ver la probabilidad. Lo mismo con el caso antiferro, solamente que modificamos la energía de enlace. Esto nomás como ejemplos. En los sistemas estudiados en esta ocasión son los sistemas. Estos tres jóvenes son interesantes, ¿por qué? Porque cada átomo interactúa de manera diferente. El hierro en casi todas sus fases interactúa de manera ferromagnética. El manganeso casi siempre interactúa de manera antiferromagnética y el aluminio es un paramagnético de toda la vida. Antiferro, paramagnético, podemos introducirlo a la expresión calculando la magnetización promedio, luego el promedio configuracional, luego la derivada y luego los igualamos. En este caso usamos clústeres de 1 y 2 spines. ¿Por qué? Por simplicidad. Ahora, sabemos además que nosotros, la magnetización nos sirve como parámetro de orden para medir los cambios de ferro a para y antiferro a para. Pero falla completamente para medir parámetro de orden para transiciones de vidrio de spin a paramagnético o de vidrio de spin reentrante. Por esta razón, para cuando vamos a calcular las transiciones de fase para estas fases, usamos el parámetro de Edward Anderson, el cual tiene la idea de la función de correlación de un spin consigo mismo. Utilizando estos dos conceptos y derivando la magnetización y igualándolos, obtenemos estas dos expresiones para la transición. Esta de para y ferro a de para ferro y de antiferro a para, y esta para las de vidrio de spin. Bueno, yo soy muy consciente que a priori no se ve tan bien, pero vamos a estudiar un poquito más de esto. Primero, positivo. Nos da todas las transiciones que necesitamos, y eso es un avance. Nos da todas las transiciones que estamos buscando. Negativo. No se puede ajustar más feo. El ajuste está muy feo, entonces no nos podemos quedar aquí. Sigamos avanzando el modelo. Porque luego se postuló esta segunda densidad de probabilidad de enlace, en donde primero consideramos enlaces ferro, pero recordemos que para obtener un enlace ferro hay que tener un átomo de hierro y un átomo de hierro. El I, multiplicación, P cuadrado. Misma idea para antiferro, misma idea para estos enlaces cruzados, puesto que también pueden existir hierro, manganeso, ¿por qué no? Y también puede ser manganeso hierro, por eso el 2 de aquí, porque hay dos posibilidades. Y estas son todas las mundo de configuraciones que se puede tener con aluminio. Segunda cosa que hicimos, recordemos que según las investigaciones de Best-Slater, sabemos que la energía de enlace de partículas no es una constante, depende de la distancia interatómica, Luego entonces nosotros, como sabemos que la distancia interatómica dependía de la concentración, hicimos, eso sí, fue un machetazo horrible que hicimos, y es que hicimos que la energía de enlace dependiera linealmente de la concentración del material, logrando esas dos expresiones, llegando a este ajuste de aquí abajo. El cual no les voy a mentir, me siento orgulloso. Es un muy buen ajuste y pues le da validez al modelo que estamos usando. Pero si no están muy convencidos, tratemos con un sistema diferente. ¿Qué tal el sistema hierro-aluminio? Es mucho más simple. Hierro es ferro, aluminio, paramagnético. Su densidad de enlace simple, de esta forma. Encontramos una ecuación de esta forma. Hacemos que la energía de enlace igual sea función lineal de la concentración y obtenemos esta gráfica de aquí. Que pues, no les voy a mentir, no está fea, pero tampoco está muy linda que digamos. No obstante, ya que tenemos un ajuste para la energía de enlace, pensamos, bueno, ¿por qué no vemos qué pasa si metemos esto en un Monte Carlo? Buscamos un Monte Carlo que no fuera tan complicado porque es una primera aproximación al sistema. Entonces usamos el modelo, el algoritmo de Metrópolis con la energía de enlace que habíamos ajustado de los grupos de renormalización y obtuvimos este diagrama. Que si bien vemos que hay distancias considerablemente altas entre... Listo. Considerablemente altas entre teórico, experimental y simulado, es una primera aproximación, por ende no está tan mal. Ahora, como tenemos datos de temperatura contra concentración, y usando esa ecuación que nos bota el método que utilizamos, podemos encontrar una aproximación a la energía del enlace con datos experimentales. Y aquí usamos redes neuronales. Usando ajuste con redes neuronales, recuerden que yo les dije que la mayor falencia del método era que nosotros imponíamos la linealidad de la energía de enlace. Pues usando redes neuronales podemos decir que sean lo que ellos quieran. Entonces, haciendo un ajuste con redes neuronales, utilizando el método de Adams, que es un método de descenso del gradiente de la función de pérdida, obtuvimos este ajuste para la energía con esta gráfica para la magnitud de la función de pérdida, llegando finalmente a esta diagrama de fase para el mismo sistema hierro-aluminio, donde utilizamos una energía de enlace ajustada con Machine Learning. ¿Cuál es el siguiente paso? Queremos meter en una simulación, maybe un poquito más potente que el Monte Carlo, un poquito más potente que el Metrópolis, esta energía de enlace que no está limitada que no está limitada a ser simplemente lineal. Y ya. Gracias por la atención.
Bueno, gracias. ¿Preguntas? No, bueno, entonces sigamos con la siguiente charla. Gracias de nuevo a Juan Esteban. Don Estoquis Valle Andrés Rosales Rivera, de la Universidad Nacional en Manizales. Andrés, ¿no está Andrés por aquí? Sí. Sí. Pero Andrés no está, qué raro. Está aquí. Bueno, sigamos con Robert Salazar. Robert, going to talk about the comparative analysis of surface charge density in metallic layers, molecular dynamics, and method of moment approach for long-range interactions.
Les cambiamos el nombre de esta oficina.
Salazar.
pointer. You can take it.
So my intention is just to show some results of a working project regarding the molecular dynamics simulations and the way we have to reproduce electrostatics in a home system. Okay. Nice, thank you. Okay, so this is the system. It's composed by two layers. A circular layer, which has particles of charge Q, and an outer layer, which has other particles with different charge in general. And these particles interact via a column-like potential. And we include also the hard disk interaction to avoid overlapping, even when the radius of the particles B is small with respect to the size of the whole system. And there is no background density, so sometimes the system is not globally neutral. And this system can be also studied in the point of view of electrostatics. In this case, it's simpler. We have only two metal layers with different potentials, and that's all. So according to electrostatics, we have to solve the equation de Poisson for the potential and surface charge density. So it's possible to write that in integral form. This is the solution. Of course, we are not able to use the solution because we don't know the sources. So okay, what are our questions? We would like to reproduce electrostatics with moving point charged particles, and we have questions about we can do that. We can reproduce the electrostatics, yes or not. What is the role of temperatures in this direction? And we would like also to know if there is any relationship between the charge and the voltages set on this system. So starting with the part of electrostatics, we use the method of moments to solve the problem. This method is very old. It's usually employed for modeling the radiation of an antenna in classical radiation. And we use that to solve this electrostatic problem. We start by using the integral representation of that. And our goal is just to find the surface charge density. And here, this is just the distance between two different element chargers. And we may use the symmetry of the system just to simplify that. We use this symmetry. Then these integrals can be grouped, the angular part in a single integral, this one. And this integral is related with the complete elliptic integral of the first kind. It's not difficult to show it. It's just to do this type of displacement. So if we define these functions, we may look at the square distance between particles, and after some algebraical simulation manipulations, then we obtain that. And if we replace this here, we can identify quickly that there is a elliptic function divided the distance between radial distance between particles. And this is no problem if u is equal to u prime, because even when this term goes to infinite, the elliptic function goes faster to 0, so this converge. Okay. Okay, here. And the second step is to define two basis functions, one in the inner ledger, another in the outer ledger. These functions, we have taken the piecewise functions, where other sources are possible. And we expand the surface charge densities in the both bases, because it's necessary, because both ledgers communicate each other. And when we do that, then we may take the previous integral and organize the whole problem in a linear set of algebraic equations, where we may compute a matrix with which includes these functions. And once the system is inverted, we have the surface charge density. Okay. Typically, these are the results depending on the density of the bases. We have a few bases. These are the results for the surface charge density in the inner ledger, and this is the gap. This is the gap, and right there is the surface charge density of the other ledger. If we increase the number of bases, the results are better, and we write something like that. In order to interpret this plot, this tells that there is some concentration of particles here. There is a gap, and there's another concentration of negative particles here. Particles with negative charge. And here is another concentration. When we set the potential like this. And this may be verified by using molecular dynamic simulations. Here's one in the strong coupling regimen. So we see that eventually, if particles are very coupled, then we have a large concentration here of particles, here another one, and here another one. So we know that this is in the strong coupling regimen because a lot of particles are practically frozen. You see, the speed distribution tells that. Of course, this is not the ground state of the system. There is some temperature there. And if we want to find the surface charge density, we simply count particles, and we do a fit, not a fit, a comparison between the results of molecular simulations and the electrostatics. You see that in the inner ledger, there is a good agreement that in the outer one is not. In the same history, we see, for instance, the integrated charge. This is the number of charge in a circular region of radius u. And in the inner ledger, we have good agreement, but here you see that there is not a good agreement because there is an stir. This stir occurs because when we count particles in the outer ledgers, sometimes we shift these rings of particles, and we add a lot of particles instantaneously. And so here there is some result. We arrive here, up, there is a sudden increase of the number of particles. And for this reason, we have here a stair. And if you count the number of the rings here, we have 1, 2, 3, 4, 5. These are just the number of the scales of this stair. So in fact, this is a finite size effect because we have only 1,000 particles in the simulations. Let me see. Okay. ¿Cómo? Ahí. Is it different? No. Oops. Tenía el sistema. Yo qué habré hecho. Sí. we try again. So this slide. So, okay. Okay, it's possible also to do some comparisons with the electric field, the potential in the space. And to compute that, we use this formula. And once we approach to the, okay. Once we approach to the layers, we see this behavior. And in fact, you see these flat regions are just the layers, the metallic layers. And this is just a cross section of this plot. And to do comparisons of the potential is as follows. And we use a molecular dynamic simulation of 1,000 particles. We take the thermodynamic average of the potential of the particles evaluated on the sheets, and we identify these values in molecular dynamics. And with these potentials, we fit the molecular the method of moment, and we find this type of plot, and we see that in fact this thing is just that here we have some differences because you see it should be a constant because it's a metallic layer here also. And this is because the rings we showed you previously, the 1, 2, 3, 4, 5 rings. And this is just the particles because at the end the system is kept. So may okay. So in order to increase the concordance between both results, we increase the temperature until moving all the particles. We stop the increase of temperature when we have this type of distribution of the velocity, and the points corresponds to the velocity distribution of an ideal gas at a given temperature. And at this point, well, we have practically a liquid regime. And when we perform the counting of particles and to achieve the surface charge density, we see that there is a better agreement between the electrostatic results and molecular dynamics. The same with the integrated charge. And here, okay, there is still the particles, but you see it is better. So it is possible also to see other cases. For instance, we said positive charges in the inner layer and positive charges in the outer one, and these are the results. And we see that these are repulsion. There is practically no particles here, and we do a comparison between the potential in space, molecular dynamics, and metal moments have good agreement. If we interchange the signs of the individual charges, and there is a change of the potential like this, but it's essentially a change of signs also. This can be understood if we look at the electrostatic energy. This can be computed with this formula. Since the sheets have constant potential, then we arrive to this result. Just the energy required to have this electrostatic configuration is just the voltage of the inner layer by its charge plus the voltage of the outer by its charge. But we know also that okay, this will generate electric field in the space, and we know that this energy should be positive. So we have this condition for the voltage and charges. So this implies that for different charges, we have to fulfill that, and for equal charges, we have to fulfill that. So if we have positive charges, this positive plus plus, then this could be positive, this sum, and the inequality is satisfied. Is just the first It's just that, just that. But once we change the sign of the chargers, minus, and then in order to fulfill that, it's necessary to invert the sign of these voltages. So this is the reason. And you may say, well, you are doing two numerical methods. Probably one of those methods may be wrong. So we may also do comparison with exact solutions in the limit R1 times to R2. This is the Kepler's limit, and taking the outer value and making it. And in this case, it is possible to find exact solutions by using the approach of the electric vector potential, where the electric field is not seen as minus the gradient of the potential. Instead of that, we use the curl of the rotation of a vector potential. And this vector potential, we have demonstrated that is this one. And when we obtain the curl, we obtain the electric field in a like low. So in other words, the electric field is computed as this would be a magnetic field. So when we use that for the case of the circular case, it is possible to solve exactly the electric potential, the vector potential. Again, there is some elliptic functions, and when we take the derivative of this potential, we may arrive to the supercharge density, the exact one for the case of the Kepler's limit, and we see this is the result for this case, and this is basically what happened if you take the first one I showed you here, and in the gap, and then you zero the gap, you will reproduce the same plot, which is exact. I have done the check with the method of moments. Method of moments is working well, and we have to do the same with the molecular dynamic simulations, just to be sure that all our simulations are right. And just to finish, I have to say that I do not work alone. I work with Christian Cobos, which is my student in the university, in the Department of Electric Engineering. Camilo works with me in the part of the method of moments, analytical methods. And Diego Jaramillo and Christian, they do the molecular dynamic simulations. So thank you.
Any questions? No. Thank you.
Okay.
So the last talk will be by Andrés Rosales.
Okay. Buenas tardes. Muchas gracias a Gabriel y a José Daniel por invitarme a este bello evento, al cual me gusta asistir, he tenido la oportunidad de asistir en la tercera o cuarta ocasión. Esta oportunidad voy a presentar trabajos denominados efectos de frustración sobre el comportamiento magnético de una aleación basada en hierro, cromo, cobre, niobio, silicio, boro, sobre el camino de percolación. Es un trabajo realizado en el grupo de magnetismo de materiales avanzados de las sales, de donde vengo, y en el cual han participado diferentes estudiantes a nivel de pregrado, maestría y doctorado. En este cuadro acá tenemos varios aspectos ilustrativos de la ciudad de Manizales y de la universidad. rápidamente un contenido del trabajo, motivación, propósito, aleaciones magnéticas, ruta tanto experimental como algunos elementos teóricos, resultados, y hablar un poco sobre los exponentes críticos, anisotropía magnética, efecto Hall, efecto Hawkinson, interpretación y los agradecimientos. Vamos de forma muy rápida. Nuestro interés, nuestra motivación es trabajar sobre vidrios metálicos. Vidrios metálicos son unas aleaciones preparadas por un método que se llama Mel-Spin, y es que quedan en forma amorfa. Se llaman vidrios porque los átomos no alcanzan a ordenarse de manera organizada. Tienen unas propiedades magnéticas bien interesantes, son propiedades magnéticas blandas, lo que significa que tiene una respuesta rápida a un campo magnético pequeño, se magnetizan y se magnetizan muy rápidamente, y logrando entonces o ser apropiadas para aplicaciones en sensores y en transformadores, ya que tienen muy pocas pérdidas de energía. Nuestro propósito es ganar entendimiento sobre el comportamiento crítico magnético, interacciones magnéticas y algunos otros efectos como efecto Hall, efectos de frustración, y estudiar el sistema en el límite de percolación. Nuestra ruta es los materiales preparados, algunas herramientas experimentales para estudiarlos como magnetización, efecto Hall, anisotropía magnética. Son técnicas bien establecidas y relativamente sencillas, y acompañado de algunos elementos teóricos para tratar los exponentes críticos, determinar los exponentes críticos y mirar los efectos o los posibles efectos que tienen interacciones sobre esos exponentes críticos y los resultados. Hemos tomado la aleación de hierro, cobre, niobio, silicio, boro como punto de partida. Es una aleación introducida sobre la década del final del 80, es comercial, pero es destacada porque presenta, como lo podemos ver acá, es destacada porque tiene una alta relatividad permeativa, una alta permeabilidad que está por encima de cualquier límite de un material convencional. Es un material ya de forma industrializado, comercializado con nombre Finemet, y la pregunta es ¿por qué seguirlo estudiando si ya tiene aplicaciones industriales? ¿Sí? Entonces, el asunto allí es que me incliné para mirar de combinar este material que es ferromagnético con algún elemento como el cromo, que es antiferromagnético. Entonces, en ese sentido fue en vía contrario de lo establecido, porque el cromo, como es antiferromagnético, va a degradar la propiedad magnética del material. Sin embargo, he ido en esa ruta y hemos encontrado diferentes fenómenos. El material es como Finemet es tan aplicado que aquí está de un reporte de que se lanzó la aleación desde 1988 hasta el 2016, y la cantidad de artículos publicados sobre ese sistema. Entonces, nuestro propósito es hasta dónde el cromo puede degradar la cantidad de la magnetización. Dentro de los conceptos que vamos a usar está el parámetro de orden, magnetización de campo cero, los exponentes críticos denominados beta, gamma, delta, alfa, que caracterizan diferentes cantidades físicas cuando el material o el sistema está pasando de un estado ferromagnético a un estado paramagnético. Y con base o se toma este parámetro TEM, que es la temperatura reducida, que le da la desviación de la temperatura de trabajo con respecto a la temperatura crítica. Adicionalmente de eso, estos exponentes están relacionados a través de lo que se llama desigualdades de exponentes. Y entonces uno determinando dos exponentes puede determinar un tercero. Es decir, que solamente de los 4 o 5 exponentes críticos, 2 de ellos son independientes. Y usando estas relaciones podemos determinar un tercero y un cuarto exponente. Y también un concepto de hipótesis de escalamiento. Rápidamente, las rutinas o los métodos para determinar los exponentes críticos es a partir de medidas de magnetización en función de campo a temperatura constante. Esto es un método empleado principalmente cuando el material es cristalino y tiene solamente una temperatura crítica. En el caso particular de nosotros, trabajamos con sistemas amorfos, entonces también trabajamos con otro método, el método del profesor Campillo, de la profesora Campillo-Berger, es un método que es para materiales amorfos, en el sentido de que tiene una distribución de temperaturas críticas. Sin embargo, hemos determinado los diferentes exponentes críticos y hemos comparado los resultados obtenidos por el método de Kuhl-Fischer y el método de Campillo-Berger, y vemos que esos exponentes críticos son compatibles por ambos métodos, dan los mismos resultados con un buen tratamiento de datos. ¿Sí? Aquí están las diferentes ecuaciones, no me voy a tener en eso. En este trabajo ha participado bastante el estudiante Rafael Felipe González, desarrollando algoritmos para ajustar las medidas experimentales con base en estas ecuaciones. El método se ha aplicado a diferentes materiales que hemos trabajado. Aquí tenemos un ejemplo para una cinta basada en hierro, cobalto, y entonces aquí tenemos el valor del exponente beta, cómo funciona, y el exponente beta también para hierro y para cobalto. En el caso de hierro, ese exponente beta da 0.34, significa que tiene un comportamiento crítico modelo de Ising, mientras que para cobalto es cerca de 0.39, más cercano a un modelo Heisenberg que es 0.36. Aquí otros resultados es para la aleación pues, justamente de hierro, cromo, cobre, silicio, niobio, boro, ¿sí? Pero en este caso llevamos nomás, cambiamos hasta el 10% de átomos dentro de la red o dentro del sistema de hierro, hemos reemplazado en cantidades, partimos de 0 cromo y vamos reemplazando átomos de hierro por cromo en la cantidad de 2%, 4 hasta 10%. El trabajo que hoy presento va a ser hasta el 20%. Entonces, más allá. Esta parte acá me ilustra la forma de ver exponentes críticos usando el método de Kuhl. ¿Sí? Aquí lo tenemos para diferentes aleaciones de estas. En este sentido, esta es la aleación para hierro, para cromo 73.5, esto es para la aleación pura 73.5, esta es para cuando le retiro un poco de átomos de hierro y es reemplazado por cromo en porcentaje de 2%, esta es para 10% y esta es para 18%. ¿Sí? Entonces, a partir de estas curvas que se obtienen, primero, a partir de medidas de magnetización en función de campo, se hace el tratamiento y se obtienen los diferentes exponentes críticos determinados de las pendientes de estas líneas rectas. Y donde cruzan estas dos pendientes, donde se cortan, determina la temperatura crítica. Aquí está el resumen del trabajo, ¿sí? Entonces, en esta parte que acá, tenemos el valor del exponente beta, el exponente gamma, y en este acá tenemos la temperatura crítica, en función de la concentración de cromo hasta de 0 al 20%. Entonces, estos puntos que acá me representan los valores que va asumiendo el exponente beta en función de la cantidad de cromo. Entonces, uno observa que él parte de un modelo de Ising, pasa por un modelo de Heisenberg y tiende a un modelo de campo medio donde el valor del exponente beta para campo medio es 0.5. Simultáneamente, se determina entonces el exponente de la susceptibilidad inicial térmica, que es el exponente gamma. ¿Sí? Entonces, el parte corresponde a un valor de 1.20, que es modelo de Ising, sube un poco a un modelo de Heisenberg y después tiende a bajar a un tipo de valor de campo medio que es alrededor de 1. En el caso de la temperatura de transición, que está representado por los puntos en verdes, entonces uno observa que a medida que aumentamos la concentración de cromo, la temperatura crítica disminuye. Eso me está significando que la temperatura crítica es determinada por los tipos de interacción de intercambio que hay en el sistema. Entonces, a medida que va aumentando la cantidad de cromo, la temperatura crítica disminuye, significando que la interacción de intercambio se está debilitando. Y el cambio en los valores de los exponentes críticos da la oportunidad o está indicando que adicionalmente a la interacción de intercambio entre los momentos magnéticos pueden estar activas otras interacciones, como la interacción spin-órbita, la interacción RKKY y los efectos de desmagnetización a través de la interacción bipolar magnética. Entonces, para eso estudiamos, bueno, esta es evolución de la magnetización con la cantidad de cromo. Y aquí está entonces principalmente un ordenamiento ferromagnético. Esta es para la muestra con X igual a 0, esta es para la muestra con X igual a Y, las curvas en esta corresponde a diferentes campos. Aquí tenemos para una muestra de hierro 55. Uno observa que el comportamiento magnético es completamente diferente, ¿sí? A medida que le estamos aumentando la cantidad de cromo. Y aquí hay una pequeña anomalía que se observa de mucha mejor manera en otra muestra que a continuación voy a presentar. Entonces, esta es la muestra de mayor cantidad de cromo, de hierro 53.5, y este pico se encuentra en la literatura que puede reflejar la emergencia de un pico denominado pico Hawkinson, que es descubierto hace más de 100 años, pero no se ha trabajado bastante en su significado. Y entonces, él aparece dentro de la forma teórica de explicación, aparece es que cuando el material está llegando a la temperatura crítica, él puede perder anisotropía magnética, ¿sí? Y de esa forma la susceptibilidad aumenta muy fuertemente. Entonces, para eso tomamos en este caso la derivada de la magnetización dividida por el campo, un tipo de susceptibilidad, ¿sí? Y entonces encontramos que justamente se encuentra un pico, y este pico se sitúa un poco antes de la temperatura crítica, ¿sí? En este caso, la temperatura crítica para esta cinta vale 260, aproximadamente 260 grados Kelvin, y este máximo pico se presenta en 254. Entonces, hay un desvanecimiento de la anisotropía magnética que lleva a un aumento sorprendente en la susceptibilidad. Aquí, entonces, como decía previamente, hemos acompañado con medidas de anisotropía magnética. Entonces, para hacer las medidas, esta me está representando la cinta, el material en forma de cinta, ¿sí? Entonces, en este caso, colocamos el campo magnético para medir la magnetización a la dirección de la longitud de la cinta. Y también lo podemos hacer, supongamos que esta es la cinta y el campo magnético lo colocamos perpendicular. Entonces, de esa forma podemos determinar la anisotropía del material, ¿sí? La anisotropía magnética. Entonces, en este caso, tenemos que esta es la respuesta cuando el experimento lo hemos hecho con la cinta colocada perpendicular al campo magnético, y esta que es la respuesta cuando lo hemos hecho en la dirección longitudinal, ¿sí? Entonces, esta área encerrada por estas dos curvas me representa a mí, es proporcional a la anisotropía magnética del material. Entonces, hemos encontrado que esta anisotropía está disminuyendo a medida que aumentamos la cantidad de concentración de cromo. La anisotropía magnética está relacionada, o el mecanismo para tener anisotropía magnética se refiere a la interacción spin-órbita. Entonces, lo que estamos explicando es que a medida que aumente la cantidad de cromo, esta anisotropía magnética disminuye. Lo que me está implicando a mí es que la interacción spin-órbita está disminuyendo, está siendo debilitada con el aumento de la cantidad de cromo. En este caso, tenemos aquí experimentos de efecto Hall, ¿sí? Entonces tenemos el efecto Hall en función del campo magnético. Aquí está un esquema de cómo medirlo. Entonces nosotros encontramos que la curva inicialmente para bajos campos magnéticos sigue un comportamiento lineal. Ya a medida que el campo magnético va aumentando, el gradiente va disminuyendo, el gradiente de crecimiento va disminuyendo hasta entrar en otra región. Entonces aquí tenemos claramente dos regiones que tienen una linealidad. En esta región, desde este campo, que le estamos llamando campo de cruzamiento, hacia abajo, está presente el efecto Hall extraordinario, y también tiene contribución de fuerza de Lorentz. Mientras que en la parte superior, o sea, para campos superiores a este valor, entonces está predominando simplemente la fuerza de Lorentz con un efecto Hall normal. Entonces nosotros hemos determinado para cada una de estas muestras este campo de cruzamiento. Ahora, la emergencia del efecto Hall extraordinario está relacionado también con la interacción spin-órbita. Entonces nosotros hemos relacionado aquí, en este gráfico, este campo de cruzamiento hasta dónde, el campo de cruzamiento me está indicando hasta dónde está siendo una contribución fuerte la interacción spin-órbita. Y nosotros vemos que entonces disminuye, esa interacción spin-órbita disminuye a medida que la cantidad de cromo aumenta. Entonces tenemos el experimento de anisotropía que me dice lo mismo que el experimento de efecto Hall. Entonces, como conclusiones, no, pero sí algunos comentarios. Los exponentes críticos dependen de si la interacción que está activa allí es de corto o largo alcance. La interacción spin-órbita es de corto alcance, la interacción de intercambio es de corto alcance, y eso me lleva a modelos convencionales tipo Ising o tipo Heisenberg. Mientras que la interacción es de largo alcance me lleva a modelos de campo medio. Entonces, el hecho que los valores de los exponentes críticos estén variando desde modelos convencionales hasta modelos de campo medio, lo que me está indicando es que las interacciones magnéticas, la intensidad están cambiando a medida que la cantidad de cromo está aumentando. ¿Sí? Ahora, el cromo es antiferromagnético y el hierro es ferromagnético. Entonces, hay una competición entre ellos, lo que puede dar lugar a que el sistema, a medida que está aumentando la cantidad de cromo, esté siendo frustrado. Entonces, es un efecto de frustración. Adicionalmente, como estamos trabajando cerca, si ustedes observan acá con cuidado, este campo magnético aquí, en esta que acá, tiende para cero o tiende para muy pequeño a medida que la concentración de cromo aumenta bastante. ¿Sí? Y eso tiene un sentido. Es decir, lo que me está diciendo es que el efecto Hall extraordinario está disminuyendo. Entonces la pregunta es, ¿hasta qué cantidad de cromo va a disminuir? O sea, ¿hasta qué cantidad de cromo el sistema va a soportar para convertirse no un material ferromagnético en un material paramagnético completamente? ¿Sí? Entonces, aquí tenemos algunas conclusiones. En las muestras con X igual a 0,2, el comportamiento crítico es tipo Ising. Otras muestras para X igual a 4 es Heisenberg. Para mayor que 6, tipo campo medio. Y el cromo entonces juega un papel importante en las propiedades magnéticas del material. La anisotropía magnética decrece a medida que, y el efecto Hall también decrece, extraordinario decrece, a medida que la interacción, la cantidad de cromo va aumentando. Eso me está indicando una activación de series de intensidades de interacciones magnéticas, ¿sí? Y pues, hay posiblemente un vidrio tipo de spin. Además de eso, se ha mostrado la existencia de la interacción del pico Hawkinson, ¿sí? El paso siguiente en el caso de nosotros es mirar si somos capaces de plantear un hamiltoniano que me pueda describir el comportamiento del sistema. Esto es una fotografía de las personas que integran el grupo y en el cual le han dado una fuerte colaboración. Este trabajo, desde luego han participado varios estudiantes de la maestría de pregrado y doctorado, diferentes profesores a nivel nacional e internacional que me han colaborado, principalmente dándome muestras. Y le doy muchas gracias de nuevo a José Daniel, a Gabriela, a ustedes por su atención, y aprovecho la oportunidad para informarles e invitarlos que del 13 al 17 de noviembre vamos a hacer la tercera escuela colombiana de magnetismo en Manizales. Sean ustedes todos bienvenidos. Muchas gracias. ¿Preguntas?
Entonces, el cromo no solamente baja la susceptibilidad, sino que también cambia la anisotropía, ¿cierto?
Cambia la anisotropía.
¿Y qué ventaja tiene echarle cromo? O sea, ¿lo hace más maleable el vidrio?
Lo puede ser más resistente a la corrosión.
Ah, ok.
Al material.
Ya.
¿Sí? Ahora, él degrada la propiedad magnética.
Sí.
¿Sí? Entonces la pregunta es, ¿para qué estudiarlo si va a degradar la propiedad magnética? Sino porque pueden plantear otros fenómenos.
Sí, sí, sí.
Como por ejemplo, magnetopesa gigante, es por el cual el material, tenemos un material, le hacemos pasar una corriente AC y lo colocamos en presencia de un campo magnético muy pequeño, entonces la impedancia cambia violentamente. ¿Sí? Y eso tiene aplicaciones para sensores.
Ah, ok.
Porque la impedancia cambia fuertemente. Entonces, la cuestión del cromo es para fortalecerlo contra corrosión.
Sí.
¿Sí? y adicionalmente pues otros fenómenos se han encontrado.
O sea, el cromo, con el cromo el material presenta magnetoresistencia.
No, magnetoimpedancia, no tanto magnetoresistencia,
Ah,
sino
magnetoimpedancia.
magnetoimpedancia.
Ah, ya, listo. ¿Ve?
Gracias.
Muy interesante.
Gracias.
Muy completo el
Daniel.
trabajo.
Ah, yo me pregunto.
Mencioné que la interacción spin-órbita se puede reducir al
incrementar la cantidad de cromo.
Con cromo.
Sí.
Eso se verifica mediante el efecto Hall. ¿O cómo
Mediante
se
efecto
verifica
Hall, mediante efecto Hall y anisotropía magnética. Porque es que la anisotropía magnética y el efecto Hall, el mecanismo que se está siendo responsable para el surgimiento de anisotropía magnética y efecto Hall es la interacción spin-órbita. Sí, es el mecanismo. ¿De acuerdo? Es por eso entonces que hacemos experimentos de efecto Hall.
Ah, ok. Bueno, muchas gracias.
No, muchas gracias, profesor. Bueno, muchas gracias. Muchas gracias.
Bueno, entonces tenemos la pausa del
Discúlpeme.
almuerzo y volvemos a las 12.